Out there, in the silent, unimaginable vastness of space, spins a celestial object so dense that a single sugar cube-sized piece of it would weigh as much as a mountain. This isn't science fiction. This is a neutron star, the collapsed, furious heart of a giant star that lived fast and died young in a spectacular supernova explosion. Picture this cosmic lighthouse, a rapidly spinning beacon of intense radiation, isolated in the profound darkness millions of light years from Earth. What are the universe's most extreme cosmic lighthouses, and what profound secrets do they hold about the very fabric of reality? These are not just distant points of light. They are natural laboratories, pushing the laws of physics to their absolute breaking point and offering us glimpses into states of matter that simply cannot exist anywhere else. Their very existence challenges everything we think we know, presenting puzzles that have captivated and confounded the greatest scientific minds for decades. Today, we are embarking on a journey, a voyage to the very edges of our observational capabilities, to meet these enigmatic objects in their most remote habitats. We are going to travel across the cosmos to explore the most distant neutron stars ever detected. This journey is about more than just cataloging strange astronomical phenomena. It is a fundamental quest to understand our place in the universe. By studying these incredible remnants, we are essentially looking back in time, witnessing the final, dramatic moments of stars that died long before our own sun even ignited. Each pulse of radiation, each flicker of light from these distant sentinels, carries encoded information about the history of the elements, the strength of gravity, and the possible fate of our entire cosmos. They are the universe's way of showing off its most extreme and bizarre creations, and by seeking them out, we are answering a deeply human call to explore, to know, and to understand the grand tapestry of which we are a small but curious part. The story of these stars is, in many ways, our own story, a narrative of curiosity, perseverance, and the relentless pursuit of knowledge in the face of the unknown. To guide us on this epic exploration, we have gathered 50 incredible facts that will illuminate the nature of these distant powerhouses. These are not just dry statistics, they are mind-bending revelations that will reshape your perception of the cosmos. We will uncover how these objects warp space and time around them, how they create gold and platinum in violent collisions, and how their immense magnetic fields could erase the data from every credit card on Earth from half a galaxy away. From the physics-defying quirks of their surfaces to the cosmic messages they broadcast, each fact is a piece of a larger, awe-inspiring puzzle. So, prepare to have your understanding of the universe challenged and expanded as we count down 50 astonishing insights into the universe's most distant and mysterious neutron stars. Our journey begins with the first and most fundamental question. What exactly do we mean when we call a neutron star distant? In our daily lives, a trip across the country feels vast, but in the cosmic scheme of things, that's a journey you couldn't even measure with the most powerful microscope in astronomy. When astronomers talk about distant neutron stars, they are referring to objects millions, even billions of light years away from Earth. To put that into perspective, a single light year is the distance light travels in 1 year, moving at an almost unimaginable speed of about 186,000 miles per second. So, a neutron star just 1 million light years away is so remote that the light we are seeing from it today actually began its journey to Earth at a time when our earliest human ancestors were just beginning to walk upright. These are not neighbors, these are ghosts from the deepest cosmic past, and merely detecting their faint whisper of energy is one of the greatest technical challenges in modern science. The primary hurdle is quite simply their immense distance combined with their relatively small size. Imagine trying to spot a single, flickering candle held by someone on the moon, but then multiply that difficulty by a factor of millions. Neutron stars are typically only about 12 miles across, and while they emit tremendous amounts of energy, that signal becomes incredibly diluted and faint after traveling across the vast, empty expanse of the intergalactic medium. By the time these photons, these tiny particles of light, finally reach our telescopes, they are but a faint trickle. We can't take a picture of one in the way we can of a nearby galaxy. Instead, we detect them indirectly, often by catching the regular pulses of radiation from those that spin, known as pulsars, or by observing the energetic bursts of X-rays or gamma rays they can produce. It's like trying to study a distant ship by only the brief, rhythmic flash of its lighthouse beacon through a thick, cosmic fog. Every piece of data we gather is a hard-won victory against the sheer scale of the universe. So why go to all this trouble? Why dedicate immense telescope time and brilliant minds to find these needles in the cosmic haystack? The answer is that these distant objects are far more than just celestial curiosities. They are unparalleled natural laboratories. The conditions within and around a neutron star are so extreme that they are impossible to recreate in any particle accelerator or supercomputer on Earth. At their cores, matter is crushed to densities where the very rules of nuclear physics break down, potentially forming exotic soups of quarks or other strange particles. By studying the light and the timing of pulses from a distant neutron star, we are effectively probing these states of matter directly. Furthermore, because the light from a neutron star billions of light years away has been traveling for so long, it allows us to look back in time. We can observe the population of stars that lived and died in the early universe, teaching us about the life cycle of the very first generations of stars and the production of heavy elements like gold and uranium that were forged in their violent deaths. Each distant neutron star is a cosmic messenger carrying encoded information about the history, the structure, and the most fundamental laws of the cosmos itself. Building on our understanding of just how remote these objects can be, we come to a true champion of cosmic distance. The current record holder for the most distant neutron star ever observed is an object officially catalogued as ULEX 1 in the galaxy GNZ 11. This staggering beacon of energy is located an incredible 13.3 billion light-years away from Earth. To fully appreciate that number, consider that the universe itself is only about 13.8 billion years old. The light we are detecting from this neutron star began its journey to us when the cosmos was in its absolute infancy, a mere 500 million years after the Big Bang. It is a relic from the era of the very first stars, a time often called the Cosmic Dawn. The discovery was made using the combined power of NASA's Chandra X-ray Observatory and the Hubble Space Telescope, with crucial data later coming from the James Webb Space Telescope, which is perfectly suited for peering into these deepest reaches of space and time. Determining a distance this vast relies on a fundamental concept in cosmology known as redshift. As the universe expands, it stretches the very fabric of space itself. Light waves traveling through this expanding space get stretched along with it, causing their wavelength to shift toward the red end of the electromagnetic spectrum. The greater the distance the light has traveled, the more the space has expanded during its journey, and the more extreme its redshift becomes. For GNZ 11, the redshift measurement is so profound that it places it at the very frontier of our observational capabilities. Astronomers weren't just looking for a faint point of light. They were analyzing the specific signature of the host galaxy's light, seeing how much it had been stretched from its original state. This precise measurement allowed them to calculate the phenomenal distance with remarkable confidence. Finding a neutron star at this distance is not just a record-breaking stunt. It is a profound achievement that challenges our understanding of stellar evolution. The existence of such an object so early in the universe's history tells us that the first generations of stars were not only immense and short-lived, but that their deaths in supernova explosions could indeed leave behind these dense, rotating remnants. It forces us to reconsider the timelines for how quickly the universe could forge the heavy elements necessary for planets and life. Before this discovery, it was an open question whether conditions in the early cosmos allowed for the formation of neutron stars, or if the first stars collapsed directly into black holes. The persistent X-ray emission from ULX-1, a signature of a neutron star's intense activity, provides a definitive answer. It confirms that the universe was already building these incredible cosmic powerhouses and lighting up the darkness almost from the very beginning. Detecting these cosmic specks from billions of light years away is a monumental feat of engineering and ingenuity. Astronomers don't simply point a telescope and see a neutron star like a nearby planet. They have to become cosmic detectives, interpreting subtle clues in the light that finally reaches us. The primary methods rely on catching these objects in the act of doing something energetic, typically by focusing on the specific types of radiation they emit most strongly, X-rays and radio waves. Our everyday optical telescopes are almost useless for this deep space hunt, as the visible light from such a distant, small object is far too faint. Instead, we use specialized observatories that can see the high-energy universe. The most common way a distant neutron star betrays its presence is through pulsar activity. When a neutron star is born spinning rapidly with a powerful magnetic field, it can become a pulsar. Think of it not as a steady star, but as a spinning cosmic lighthouse. The intense magnetic fields funnel radiation into two powerful beams that shoot out from the magnetic poles. If these poles are misaligned with the star's rotation axis, the beams sweep through space like the beacon of a lighthouse. From our distant vantage point, we see this as a perfectly regular, rapid-fire pulse of radiation each time a beam sweeps across our line of sight. These pulses can arrive with a precision that rivals atomic clocks, creating a distinct, repeating signature that astronomers can pick out from the background noise of the cosmos, even across immense intergalactic distances. It's a rhythmic tap, tap, tap from the void, an unmistakable calling card. The other major detection method involves X-ray observations, particularly of systems known as X-ray binaries. This is often how we find the most distant neutron stars, like the record holder in galaxy GNZ 11. In an X-ray binary, the neutron star has a companion, a normal star. The neutron star's immense gravity acts like a cosmic vampire, relentlessly pulling gas away from its stellar partner. This stolen gas doesn't just fall gently onto the surface. It spirals in at tremendous speed, forming a superheated disk of material around the neutron star called an accretion disk. The physics of this process are extreme. The gas in the disk is heated to millions of degrees, causing it to glow not with visible light, but with incredibly energetic X-rays. This transforms the entire system into a brilliant, high-energy beacon that our X-ray telescopes can detect from much farther away than a solitary pulsar. By analyzing the flickering and the spectrum of this X-ray light, scientists can deduce the properties of the invisible object pulling in the material, confirming it is a neutron star and not a black hole. None of this would be possible without revolutionary technological advancements. For X-ray astronomy, the workhorse has been the Chandra X-ray Observatory. Launched into orbit in 1999, Chandra was specifically designed to see the universe in X-rays with unprecedented clarity. Because Earth's atmosphere blocks X-rays, telescopes like Chandra must operate in space. Its resolution is so sharp it's often compared to reading the text of a newspaper from half a mile away. Chandra's sensitive instruments can pinpoint the faint X-ray glow of a distant neutron star binary, allowing astronomers to measure its brightness and study its behavior over time. In the radio part of the spectrum, vast arrays of radio dishes, like the Very Large Array in New Mexico or the upcoming Square Kilometer Array, act as enormous ears, listening for the faint, rhythmic pulses from distant pulsars. These observatories don't just collect light, they collect data points that, when pieced together by powerful computers and brilliant analysis, reveal the stories of these otherwise invisible titans. Now let's turn to one of the most mind-bending properties of neutron stars, a feature that truly sets them apart from any other object in the cosmos, their almost incomprehensible density. To grasp this, picture the entire mass of a star at least 1.4 times more massive than our Sun, a colossal sphere of incandescent gas millions of miles across, being crushed by the force of its own gravity down into a perfect sphere only about 12 miles in diameter. That's like compressing Mount Everest into a single grain of sand, or squeezing every single person on Earth into a single raindrop. This results in a density so extreme that a single teaspoon of neutron star material would weigh not just tons or thousands of tons, but a staggering 5 billion tons here on Earth. That's roughly the mass of every human being alive today, all packed into a volume you could hold on a spoon. This isn't ordinary matter anymore. It's a neutron-rich fluid so compact that the atoms themselves have been utterly destroyed, with electrons crushed into protons to form a super-dense sea of neutrons. The direct consequence of this phenomenal density is a gravitational pull at the surface that defies all earthly experience. If you were to somehow stand on the crust of a neutron star, a feat impossible for many reasons, you would experience a gravitational force 100 billion times stronger than what we feel on Earth. Your body would weigh more than the entire human population combined, and you would be instantaneously flattened into a layer just one atom thick. This gravity is so powerful that it dramatically warps the path of light itself. If you could look at one from the side, you would see not just the front hemisphere, but also light bending around from the back, allowing you to see more than 50% of its surface at once. It's a natural demonstration of Einstein's theory of general relativity playing out on an epic scale. And this gravitational intensity leads to one of the most famous and terrifying phenomena in all of astrophysics, spaghettification. Imagine an object, perhaps a rogue asteroid or even a whole moon, drifting too close to a neutron star. The force of gravity on the side of the object nearest the star is exponentially stronger than the force on the far side. This difference in pull, known as a tidal force, would stretch the object out into a long, thin stream of material, just like a piece of spaghetti. Every mountain, every boulder, every single molecule would be pulled apart in a line directly toward the star before being vaporized and added to the neutron star's mass. It's a brutally efficient and violent process that demonstrates the raw, unbridled power of gravity in its most extreme form. This incredible compactness is also the engine behind the neutron star's other great weapon, its unimaginably powerful magnetic field. As the original star collapsed, its pre-existing magnetic field became compressed and concentrated along with the matter. This is the conservation of magnetic flux in action. Take a magnetic field that was once spread across a vast volume and squeeze it into a space a billion times smaller, and its strength increases astronomically. The result is a magnetic field that can be a quadrillion times stronger than Earth's protective magnetic shield. These are the magnetars, the magnetic superstars of the cosmos. A magnetar's field is so intense that it could wipe the data from every credit card on Earth from a distance of half the moon's orbit away. It can literally twist the atomic structure of matter, creating a crust under such stress that it occasionally cracks, releasing starquakes that unleash flashes of gamma rays more energetic than our Sun will emit over its entire 10 billion-year lifespan. These brief, catastrophic events are among the most powerful explosions detected since the Big Bang, all born from the unimaginable density locked within these distant, spinning cinders. But to truly appreciate the journey of these distant neutron stars, we must first understand their dramatic and violent birth. Every one of these cosmic powerhouses begins its life in one of the most energetic events in the entire universe, a core collapse supernova. This is not a gentle fading away. It is the spectacular death of a star at least 8 times more massive than our own Sun. For millions of years, such a star burns through its nuclear fuel, fusing hydrogen into helium, then helium into carbon and oxygen, building progressively heavier elements layer by layer in its core like a cosmic onion. This process is a constant battle, with the intense heat and pressure from fusion pushing outward, while the star's own immense gravity pulls everything inward. For the star's entire life, this balance holds, but it is a fragile truce. The end comes swiftly. Once the star begins forging iron in its core, the game changes completely. Unlike all previous fusion reactions, fusing iron does not release energy. It consumes it. Suddenly, the core has no outward pressure from fusion to support itself against the crushing weight of the outer layers. In less than a second, the balance shatters, gravity wins. The core, which may be the size of Earth, catastrophically collapses inward at speeds approaching a quarter of the speed of light. In this unbelievable implosion, electrons are literally forced into protons, transforming them into neutrons and releasing a flood of ghostly particles called neutrinos. The entire core is compressed from a sphere thousands of miles wide into a city-sized ball of pure neutrons, a proto-neutron star. The collapse halts only when the density becomes so extreme that the neutrons themselves, governed by quantum mechanical laws, simply refuse to be packed any closer together. This creates a phenomenon known as neutron degeneracy pressure, an immense outward force that suddenly stops the core's collapse dead in its tracks. The story doesn't end there. The inner core may have stopped, but the rest of the star is still falling inward at tremendous velocity. This outer material smashes into the newly formed, incredibly hard surface of the neutron star core and rebounds in a titanic shockwave. This rebounding shock, supercharged by the immense energy of the escaping neutrinos, ripples back outward through the star's layers. The result is a cataclysm of almost unimaginable power. The star is literally blown apart from the inside out in a supernova explosion so bright it can, for a few glorious weeks, outshine an entire galaxy of billions of stars. What remains after the brilliant flash fades is the stellar corpse we've been discussing, the neutron star, and a rapidly expanding cloud of glowing gas and newly forged heavy elements known as a supernova remnant. This violent birth process doesn't just create the neutron star, it also gives it a powerful kick that can send it flying across the galaxy and sometimes right out of it. Supernova explosions are not perfectly symmetrical. Slight imbalances in the collapsing core or in the way the shockwave propagates can cause more material and energy to be ejected in one direction than in another. Think of it as a natural rocket engine. If you have an explosion that is even slightly lopsided, the recoil will push the newly born neutron star in the opposite direction, much like a balloon zooming around a room when you let the air out. These supernova kicks can be astoundingly powerful, accelerating the neutron star to velocities of hundreds of miles per second. At those incredible speeds, a neutron star can easily escape the gravitational pull of its home star cluster, becoming a runaway star. Some receive such a tremendous kick that they achieve what is known as hypervelocity, allowing them to break free from the gravitational hold of the entire Milky Way galaxy itself. This ejection mechanism is a crucial piece of the puzzle when we talk about finding neutron stars at such vast intergalactic distances. A lonely neutron star cast out from its birthplace by a violent, asymmetric supernova becomes a rogue traveler in the emptiness between galaxies. It will spend millions, even billions of years drifting through this profound darkness, a cosmic lighthouse with no shore to warn, its spin slowly ticking down as it journeys toward oblivion. When we detect one of these isolated pulsars far away from any visible galaxy, we are likely witnessing the final legacy of that ancient, powerful kick from its birth. It's a lonely existence, but it provides astronomers with pristine laboratories, free from the contaminating light and gas of a host galaxy, allowing us to study the fundamental properties of these incredible objects in perfect isolation. Among the many forms a neutron star can take, none is more iconic or revealing than the pulsar. Think of it not as a steadily shining star, but as a master of celestial illusion, a cosmic lighthouse of unimaginable power. The secret to its rhythmic flash lies in a profound misalignment. A pulsar is born from a supernova collapse that leaves behind a rapidly spinning neutron star with an immensely powerful magnetic field. Crucially, the magnetic poles of this star are not aligned with its axis of rotation. As the star spins, sometimes hundreds of times every single second, these powerful magnetic poles funnel intense beams of radio waves, light, X-rays, or gamma rays out into space. If one of these sweeping beams happens to cross our line of sight here on Earth, we detect a brilliant, fleeting pulse of energy. Then, as the star continues its rotation, the beam swings away from us and the signal seems to vanish, only to reappear with perfect regularity on the next spin. This creates the iconic pulse that gives these objects their name, a blink that makes the star appear to be turning on and off, when in reality it is emitting a continuous but highly focused torrent of radiation. The clockwork precision of these pulses is nothing short of phenomenal. The most stable pulsars, known as millisecond pulsars, rotate with a consistency that rivals the most advanced atomic clocks built by humanity. Their rotational periods can be measured with an accuracy of better than 1 part in a quadrillion, meaning they might lose or gain just a single second over tens of millions of years. This incredible stability doesn't just make them fascinating curiosities. It transforms them into powerful tools for scientific discovery. For instance, astronomers use these cosmic clocks as a galaxy-spanning laboratory to test Einstein's theory of general relativity with extreme precision. When a pulsar is in a binary system with another dense object, like a white dwarf or another neutron star, the intense gravity of the system causes slight, predictable delays in the arrival times of the pulses. By meticulously tracking these minute deviations over years, scientists can verify the predictions of relativity in ways that are impossible in any Earth-based experiment, watching as the pulsar's signal is warped by the curvature of spacetime itself. This same timing precision opens up a visionary possibility: interplanetary and even interstellar navigation. Just as sailors on Earth once used the stars to guide their ships, future spacecraft traveling through the solar system and beyond could use the predictable pulses from a network of these cosmic lighthouses to determine their position with incredible accuracy. A spacecraft could compare the arrival times of pulses from several different known pulsars. Because each pulse has a unique signature and an ultra-stable period, the slight differences in when the signals arrive at the spacecraft would allow its onboard computer to triangulate its location in three-dimensional space, creating a GPS-like system that works across the entire galaxy. This concept, known as pulsar-based navigation, would free humanity from reliance on Earth-bound tracking systems, providing an autonomous and universal method for any vessel to find its way through the deepest, darkest ocean of space, guided by the steady, reliable heartbeat of these distant, spinning sentinels. Continuing our exploration of these cosmic extremes brings us to a subject that redefines the very meaning of the word powerful. Even among the already bizarre family of neutron stars, there exists an elite and terrifying subclass, the magnetars. If an ordinary neutron star's magnetic field is impressive, a magnetar's is simply apocalyptic. To put it in perspective, Earth's magnetic field is strong enough to guide a compass needle. A typical neutron star's field is 1 trillion times stronger than that. But a magnetar, its magnetic field measures a staggering 1,000 trillion times stronger than Earth's. This is a number so large it becomes almost abstract, a 1 followed by 15 zeros. This isn't just a strong magnet, this is a force that fundamentally warps the environment around it in ways that seem like they're pulled from science fiction. The raw power of such a field is difficult to overstate. If a magnetar were to magically appear halfway between the Earth and the Moon, about 240,000 miles away, the consequences would be catastrophic. Its magnetic field would not just disrupt electronics, it would be strong enough to strip the data from the magnetic strips of every credit card on the planet. But that would be the least of our worries. The field's intense force would interact with the atoms in our bodies, magnetizing and twisting them, effectively scrambling the very biochemistry that keeps us alive from a distance of nearly 250,000 miles. It is a level of power that makes the star itself a prisoner of its own creation, with a crust locked in a state of immense stress, perpetually on the verge of a cosmic-scale catastrophe. This leads us to the most dramatic manifestations of a magnetar's existence: starquakes and giant flares. The crust of a neutron star is not a smooth, solid surface. It's a lattice of iron nuclei, 1 billion times stronger than steel. Yet it is under such unimaginable strain from the twisting magnetic field beneath it that it occasionally cracks. These are not like earthquakes on Earth. A magnetar starquake is a rupture that releases more energy than a magnitude 23 earthquake, an event so powerful it has no equivalent on our planet. When the crust fractures, it releases a titanic burst of energy, shaking the entire star and causing a sudden, brilliant flash of hard X-rays and gamma rays that can be detected across interstellar space. These starquakes are the prelude to the magnetar's ultimate performance, the giant flare. A giant flare is one of the most violent and energetic outbursts known in the universe since the Big Bang itself. In a mere tenth of a second, a single magnetar can unleash more energy than our Sun will radiate over the entire course of 100,000 years. For that brief, blinding instant, the magnetar can outshine every star in its host galaxy combined. The flare begins with an intense, short spike of gamma rays, followed by a rhythmic, fading tail of X-ray emission that pulsates with the star's rotation period, a clear signature of the event's origin. We have been fortunate enough to witness a handful of these events from magnetars within our own Milky Way galaxy. The most famous, from magnetar SGR 180620 in 2004, released a pulse of radiation that was so powerful it actually compressed Earth's magnetic field from 93,000 miles away, briefly ionizing the upper atmosphere and affecting radio communications worldwide. It was a stark reminder that the universe is home to forces that can reach out and touch us from across the gulf of space, demonstrating that the most distant and exotic objects are not just theoretical curiosities, but active, dynamic, and immensely powerful players in the cosmos. Now, let's turn our attention from the immense forces at play to something equally staggering but far more subtle: the blistering heat radiating from these cosmic embers. When a neutron star first bursts into existence in the wake of its supernova, it is born searingly hot, with a surface temperature soaring beyond 1 million degrees Celsius. To put that into perspective, that is over 150 times hotter than the surface of our own Sun. This isn't a gentle warmth, it is a furnace of such ferocity that the primary light it emits isn't the visible light our eyes can see, but an intense, penetrating glow of X-rays. This initial inferno is the direct remnant of the gravitational energy released during the core's catastrophic collapse, a final echo of the star's violent death throes. But such extreme heat cannot last forever. Isolated in the cold of space, a neutron star begins a long and inevitable journey toward cooling down, and the way it sheds this heat tells us a profound story about its internal composition. The cooling process happens through two main channels, each dominating at different stages of the star's life. For the first 10,000 to 1 million years, the most efficient cooling mechanism is the emission of neutrinos. These ghostly, almost massless particles are created in vast numbers deep within the star's super-dense core, where particles are packed so tightly they constantly interact and transform. Neutrinos have a remarkable ability to pass through almost anything without interacting. so they simply stream out from the core, carrying immense amounts of thermal energy with them directly through the solid crust and into space, effectively acting as a cosmic refrigeration system. This rapid neutrino cooling causes the star's temperature to plummet dramatically in its early youth. After this initial phase, a second, slower cooling process takes over, the emission of photons, which we observe as thermal radiation, primarily in the X-ray part of the spectrum. The star's surface, still glowing fiercely, finally becomes the main source of its cooling, radiating its remaining heat directly out into the void. This is the phase where astronomers can glean the most information. By pointing X-ray telescopes like Chandra at a distant neutron star and carefully analyzing the spectrum of its thermal glow, scientists can do something amazing. They can effectively take its temperature. This single measurement unlocks a treasure trove of data. By comparing the measured temperature with sophisticated cooling models, astronomers can estimate the star's age with surprising accuracy. A hotter neutron star is likely a youthful one, perhaps only a few 100,000 years old, while a cooler one is a venerable ancient, having drifted for millions of years. Furthermore, this thermal fingerprint reveals secrets about what's happening deep inside the star, far beneath the solid crust we can observe. The rate at which a neutron star cools depends critically on the exotic states of matter that might exist in its core. If the core is composed primarily of neutrons, it will cool at one predictable rate. However, if the immense pressure has crushed the neutrons themselves into a soup of even more fundamental particles called quarks, or if it contains exotic particles like pions or hyperons, the star will cool much more rapidly because these exotic states are even more efficient at producing neutrinos. A neutron star that is cooler than standard models predict for its age is therefore a powerful piece of indirect evidence for the existence of this strange matter at its heart. So, by simply observing the faint X-ray warmth of a distant neutron star, we are not just measuring its age, we are conducting a remote physics experiment, probing states of matter that cannot be recreated anywhere else in the universe, all from a tiny point of light billions of light years away. To truly grasp the alien nature of a neutron star, we need to venture beyond its immense gravity and magnetic fields and descend to its very surface, to a landscape unlike any other. The outermost layer of this cosmic cinder is known as the crust, and it is the closest thing the object has to a solid ground. But to call it solid is a dramatic understatement. This crust is a crystalline lattice of atomic nuclei, predominantly iron, packed together in a perfect, incredibly rigid structure. Yet this is not the iron we know on Earth. The gravitational pressure at the surface is already 1 billion times stronger than Earth's atmospheric pressure, compressing these nuclei into a formation denser than any metal found on our planet. The electrons that would normally orbit these nuclei have been completely stripped away, creating a sea of free-flowing electrons that permeates the entire lattice like a superconductive fluid. This robbing of electrons leaves the atomic nuclei positively charged, locked in place by powerful electrostatic forces, forming a substance harder than diamond and 1 billion times stronger than steel. It's a material that simply could not exist anywhere else in the universe under natural conditions. As we venture deeper, the pressure becomes almost incomprehensibly more intense. With every few inches of descent toward the core, the weight of the overlying material increases exponentially. This isn't like digging into the Earth where pressure builds gradually. Here, the crushing force is so extreme that it fundamentally alters the very identity of matter itself. The first dramatic change happens not far beneath the surface. The immense weight begins to crush the atomic nuclei in the lattice. In normal matter, atoms are mostly empty space, with a tiny, dense nucleus surrounded by a cloud of electrons. But under the neutron star's incredible pressure, that empty space is ruthlessly eliminated. The nuclei are forced closer and closer together until they are practically touching, forming a dense, solid pack of protons and neutrons. This is where one of the most critical transformations in the universe occurs, a process known as inverse beta decay. The pressure becomes so great that the sea of free electrons, which are already packed to an extreme density, are literally forced into the atomic nuclei. Inside a nucleus, an electron collides with a proton and they merge. In this incredible fusion, the two particles combine to form a neutron and release a neutrino. The neutrino, that ghostly particle, immediately escapes, carrying energy away into space. The proton, once a fundamental component of the atomic nucleus, is gone, transformed into a neutron. This process happens on a colossal scale, with electrons and protons merging relentlessly throughout the inner crust. The atomic nuclei, which started as familiar iron, become increasingly neutron-rich and unstable. They become so saturated with neutrons that they start to drip them out, creating a bizarre quantum soup where a lattice of increasingly exotic nuclei coexists with a superfluid river of free neutrons flowing between them. This marks the final transition from the solid crust to the liquid heart of the star. At a depth of about half a mile, the pressure wins its ultimate victory. The atomic nuclei can no longer maintain their structure. They are completely dissolved, and the distinction between individual nuclei vanishes entirely. What was once a crystalline solid gives way to an immense continuous ocean. This is not an ocean of water, but an ocean of pure neutrons, a superfluid possessing zero viscosity, meaning it flows without any friction whatsoever. This is the true essence of the neutron star, a state of matter so extreme that every single teaspoonful contains the mass of 1 billion tons, and it behaves according to the strange rules of quantum mechanics on a macroscopic scale. The journey from a solid crust of iron to this neutron sea is a story of matter being remade by gravity, demonstrating that in the most extreme corners of the cosmos, the very building blocks of reality can be broken down and forged into something entirely new. And now we arrive at one of the greatest mysteries in all of modern astrophysics: what lies at the very heart of a neutron star. While we can theorize about the crust and the neutron ocean, the core remains a realm of pure speculation, a place where the known laws of physics are pushed to their absolute limits and may even break down completely. The central pressures here are so astronomical that the neutrons themselves, which make up the bulk of the star, might not survive in their familiar form. Instead, theorists propose a wild menagerie of potential exotic states of matter that sound like they are pulled from the pages of a theoretical physics textbook. The core could be a neutron superfluid, a state where the neutrons flow with zero friction, creating a quantum liquid of unimaginable scale. Intermingled with this could be a proton superconductor, where protons pair up and conduct electric current with perfect efficiency, generating the star's immense internal magnetic fields. But the most radical possibility is that the very concept of individual neutrons vanishes entirely. At the core's very center, the pressure might be so overwhelmingly powerful that it overcomes the strong nuclear force, the very glue that holds neutrons and protons together. This could lead to a phase transition where the boundaries of individual neutrons dissolve. Imagine taking all those neutrons and literally squeezing them until they crack open, their constituent parts spilling out. What you'd be left with is a soup of even more fundamental particles, up quarks, down quarks, and strange quarks, all swirling together in a state known as deconfined quark matter, or a quark gluon plasma. This is often referred to as strange matter because of the presence of the strange quark, and some theories even suggest that this form of matter could be the most stable state in the entire universe, more stable than the matter we are made of. A neutron star with a quark matter core would be a truly unique object, a hybrid star with a solid crust, a neutron ocean, and a heart of pure, searing quark soup. Since we can never send a probe to drill into a neutron star, how on earth can we possibly test these fantastical ideas? The answer lies in using the entire star as a laboratory and observing its global behavior for clues about its internal structure. One crucial method is by precisely measuring how these distant objects cool down over time. As we discussed, young neutron stars cool rapidly by emitting neutrinos. But the rate of this cooling depends dramatically on what's inside. A core made of normal neutrons will cool at a certain predictable rate. However, a core that has transitioned to a quark-gluon plasma would be a vastly more efficient neutrino factory. If astronomers detect a neutron star that is significantly colder than its predicted age would suggest, it's a strong hint that exotic, rapid cooling processes are at work deep within its core, pointing firmly toward the existence of that long-theorized quark matter heart. Another revolutionary way to probe the interior is by listening to the universe itself through gravitational waves. When two neutron stars spiral inward and finally collide, they create ripples in the very fabric of spacetime. The specific shape of these gravitational wave signals is exquisitely sensitive to the internal structure of the colliding stars. A neutron star with a soft, compressible interior, perhaps dominated by a neutron superfluid, will deform differently as it spirals than a star with an extremely stiff core, potentially made of solid quark matter. By comparing the gravitational waves we detect from such cosmic collisions with millions of theoretical models, scientists can essentially perform a remote ultrasound on the neutron star, deducing the stiffness and composition of its deep interior. Every single distant merger we observe is not just a spectacular firework. It's a data point that helps us rule out some theoretical models and brings us closer to understanding the true nature of matter under the most extreme conditions the universe can muster. Just when you thought neutron stars couldn't get any more extreme, consider this. Some of them are the universe's ultimate speed demons, racing through the void at velocities that can exceed 1,000,000 miles per hour. At that staggering speed, you could travel from Earth to the Moon in less than 15 minutes. These aren't just drifting cinders, they are cosmic cannonballs, ejected from their birthplaces with such force that they become lone wanderers on an epic journey through the galaxy and beyond. This incredible motion isn't a random accident. It's a direct consequence of the most violent and asymmetrical birth process imaginable. When a massive star goes supernova, the explosion is rarely perfectly spherical. Picture a balloon with a weak spot when it pops. It doesn't just collapse inward evenly, it recoils and shoots off in one direction. A supernova does the same thing on a stellar scale. If more material and energy are blasted out in one direction during the explosion, the newborn neutron star recoils in the opposite direction, propelled by the ultimate rocket engine. This kick can be so powerful that it launches the stellar remnant at hundreds and sometimes over 1,000 kilometers per second. This phenomenal velocity has a profound consequence. It can grant a neutron star its cosmic freedom. A star receiving a typical powerful kick can easily achieve escape velocity from its home star cluster, becoming a runaway object, but the most extreme cases go even further. If the kick is perfectly aligned and powerful enough, a neutron star can reach what astronomers call hypervelocity, allowing it to break free from the gravitational grip of the entire Milky Way galaxy. Once a star crosses this threshold, there's no turning back. It leaves the bright, star-filled disk of its home galaxy behind and enters the vast, desolate intergalactic medium, the immense, dark oceans of near-nothingness that separate island universes. Here, it will drift for billions of years, a solitary beacon in the profound darkness, its spin slowly winding down as it journeys toward oblivion. When our telescopes detect a lone pulsar far away from any visible galaxy, we are almost certainly witnessing one of these hypervelocity exiles. Its great distance isn't just a measure of space, it's a testament to its ancient, powerful ejection and its eons of uninterrupted travel. The existence of these intergalactic travelers provides astronomers with a unique opportunity. Isolated from the light pollution and gas clouds of any host galaxy, these neutron stars become pristine laboratories, Studying their pulsars and their properties gives us a clean, unobstructed view of the object itself, free from any contaminating influences. Furthermore, their trajectories tell a story. By tracing their paths backward through space, astronomers can sometimes pinpoint the galactic neighborhood they were violently ejected from millions of years ago, offering clues about the types of stellar environments that produce such powerful supernova kicks. Each one is a fossil record of a cataclysm that occurred long before our solar system even formed, and by measuring their speed and trajectory, we can piece together the history of their explosive origins, adding another crucial piece to the puzzle of how these incredible objects are born and distributed throughout the cosmos. While many of these incredible objects travel the cosmos in solitary silence, a surprising number actually have a partner. In fact, astronomers estimate that a substantial portion of all neutron stars exist not alone, but in binary systems, gravitationally bound to a companion star. This cosmic dance partner can be another neutron star, creating one of the most extreme pairings in the universe, or it can be a more typical star, like a white dwarf or even a main sequence star similar to our Sun. It is within these dynamic duos that some of the most energetic and revealing phenomena in the universe unfold, turning a quiet corner of space into a brilliant, high-energy laboratory. The gravitational bond between these two objects sets the stage for a dramatic and relentless process that completely transforms how we see and study the neutron star. The central drama of these binary systems is a process known as mass transfer or accretion. Imagine two stars waltzing through space, locked in a tight orbital embrace. The neutron star, with its phenomenally powerful gravitational field, acts like a cosmic vampire. If the companion star ventures too close, or if it evolves and expands into a red giant, the neutron star's gravity begins to violently strip material away from its partner's outer layers. This stolen gas doesn't fall directly onto the surface. Instead, because the two stars are orbiting each other at tremendous speed, the conservation of angular momentum flings the material into a swirling, frenzied whirlpool around the neutron star. This structure is known as an accretion disk, and it is one of the most important and common features in all of high-energy astrophysics. The physics within an accretion disk are truly extreme. As the gas spirals inward, drawn ever closer by the neutron star's immense pull, it is compressed and heated through friction and gravitational potential energy to temperatures of millions of degrees. At these incredible temperatures, the gas can no longer emit ordinary visible light. It instead glows with an intense, piercing radiation of X-rays. This transformation is what turns an otherwise invisible neutron star into a brilliant beacon visible across intergalactic distances. The system becomes what astronomers call an X-ray binary, and the sudden appearance of a powerful, point-like source of X-rays in a distant galaxy is often the very first clue that a neutron star is present. It's like a cosmic burglar alarm going off, signaling a violent theft of matter happening in real time. This process of mass accretion doesn't just make the neutron star visible, it can also fundamentally change the star itself over millions of years. As gas from the disk rains down onto the neutron star's surface, it carries with it a tremendous amount of energy and, crucially, angular momentum. The impact of this material can re-energize an old, slow-spinning neutron star, causing it to rotate faster and faster until it becomes a millisecond pulsar, spinning hundreds of times per second. In a sense, the neutron star is being recycled by its companion, spun up to incredible speeds by the incessant torrent of falling matter. In the most extreme cases, if the accretion process continues for long enough and transfers a critical amount of mass, the accumulated weight on the neutron star's surface could even push it over the theoretical edge, causing it to collapse further into a black hole, ending its life as a neutron star in the ultimate cosmic transformation. And this cosmic vampirism, the relentless siphoning of gas from a companion star, leads directly to one of the most spectacular and frequent firework displays in the high-energy universe, the X-ray burst. Picture the surface of a neutron star, a landscape of unimaginable density where gravity is 100 billion times stronger than on Earth. Now, imagine a steady rain of hydrogen and helium, stolen from a neighboring star, showering down onto this incredible surface. This isn't a gentle drizzle, it's a torrent of falling gas, accelerated to a significant fraction of the speed of light by the star's gravity, impacting with the force of a continuous nuclear bombardment. Because the gravity is so intense, this accreted material doesn't just pile up loosely. It is compressed and packed down into a layer that grows ever denser and hotter at the base, a fossil fuel of cosmic proportions waiting for a single catastrophic spark. The trigger for this celestial detonation is a delicate and relentless race between pressure and temperature. As more and more hydrogen accumulates, the pressure at the bottom of this layer becomes astronomical. The temperature soars into the billions of degrees. Under these extreme conditions, the hydrogen nuclei begin to fuse into helium in a process known as the CNO cycle, which provides a steady trickle of energy. But the real drama begins with the helium. The hydrogen fusion produces a fresh layer of helium ash that settles beneath it, itself being compressed and heated. This helium layer continues to build, a sleeping giant of potential energy. The critical moment arrives when the base of this helium layer reaches a temperature of around 200 million degrees Kelvin. At this precise threshold, a special type of nuclear fusion called helium burning ignites, but it doesn't just ignite gently, it explodes in a runaway thermonuclear chain reaction. This is the X-ray burst. In a flash that typically lasts from only a few seconds to a minute, the entire helium layer, which can be several meters thick and contain the mass of entire mountain ranges, undergoes fusion all at once. The fusion rips through the layer in a supersonic flame, fusing helium into heavier elements like carbon and oxygen in an instantaneous, furious release of energy. For that brief, glorious moment, the surface of the neutron star can outshine 100,000 of our suns, with virtually all of that incredible energy pouring out in the form of high-energy X-rays. To an X-ray telescope like Chandra, it looks as if a new star has suddenly appeared in the sky, blazing with an unthinkable intensity before fading away as quickly as it came, the nuclear fuel utterly spent. These are not rare events. In some active binary systems, they can recur every few hours, a constant cycle of accumulation and detonation that turns the neutron star's surface into the most powerful and predictable natural fusion reactor in the known cosmos. Beyond their sheer spectacle, these brilliant flashes are an absolute gift to astrophysicists because they act as a direct probe of the neutron star's fundamental properties, its mass and its radius. The way the burst unfolds, its peak brightness, the rate at which it cools, the specific spectrum of X-rays it emits, is exquisitely sensitive to the strength of gravity at the star's surface, which is determined by its mass and radius. Think of it like trying to measure the size and mass of a distant, invisible bell by listening to the sound it makes when struck. The X-ray burst is the strike, and the resulting light curve, the graph of its brightness over time, is the sound. A more massive, compact neutron star will have a stronger surface gravity. This stronger gravity affects the physics of the burning layer and also causes a greater gravitational redshift, subtly shifting the color of the emitted X-rays. By painstakingly modeling the light curves and spectra of thousands of these bursts, scientists can perform a kind of cosmic forensics, reverse engineering the observations to pinpoint the precise combination of mass and radius that must have produced them. This is profoundly important because the relationship between a neutron star's mass and its radius is governed by its equation of state, a theoretical description of how matter behaves at these incredible densities. Different proposed models for the star's internal composition, whether it has a soft core of exotic quark matter or a stiffer core of normal neutrons, predict different possible combinations of mass and radius. By using X-ray bursts to measure these two numbers, astronomers can effectively rule out entire families of theoretical models. Every single burst is a data point that helps us constrain the true nature of ultra-dense matter, bringing us closer to answering the ultimate question of what lies at the heart of these incredible objects. It's a remarkable feat. By observing a brilliant flash of light from a binary system millions of light years away, we can perform a fundamental physics experiment that is impossible to conduct in any laboratory on Earth. Pinpointing the exact size and weight of a neutron star billions of light years away seems like an impossible task. Yet astronomers have developed several brilliant techniques to do just that, turning these distant points of light into cosmic laboratories for fundamental physics. One of the most direct methods relies on the spectacular X-ray bursts we just explored. The characteristics of these brilliant flashes, specifically how quickly they rise to peak brightness and how they cool down afterward, are like a secret code that reveals the surface gravity. A more massive and compact star will have a stronger gravitational pull, which affects the nuclear burning processes and how the hot material expands and radiates its energy away into space. By meticulously modeling the light curve and the subtle shifts in the X-ray spectrum caused by gravitational redshift, scientists can reverse engineer the observations to find the unique combination of mass and radius that must have produced the burst they witnessed. It's a painstaking process of matching theoretical models to real-world data, but each successful fit gives us a crucial data point in our quest to understand the nature of ultra-dense matter. Another incredibly precise method involves listening to the cosmic clocks known as pulsars, especially when they are in a binary dance with another dense object like a white dwarf or another neutron star. In these systems, the orbital dynamics become a pristine testing ground for Einstein's theory of general relativity. As the two objects orbit each other, they cause tiny, rhythmic delays in the arrival times of the pulsars' incredibly regular pulses. These delays aren't random. They are caused by effects like the Shapiro time delay, where the signal from the pulsar is slightly slowed as it passes through the curved spacetime around its companion, and the emission of gravitational waves which slowly saps energy from the orbit. By tracking these minuscule timing variations over years, sometimes even decades, astronomers can measure the masses of both objects in the system with astonishing accuracy, often to within a fraction of a percent. This gives us a direct and reliable measurement of a neutron star's mass, which is a fundamental parameter for testing any theory about its interior. The most revolutionary tool for this cosmic investigation has arrived with the dawn of gravitational wave astronomy. When two neutron stars spiral inward and finally merge, they create ripples in the fabric of spacetime itself, and the detailed shape of this gravitational wave signal is a goldmine of information. Just before the merger, as the two stars are distorted by each other's immense tidal forces, the waveform carries a clear imprint of each star's deformability, which is directly related to its internal stiffness or equation of state. A star with a soft interior, perhaps dominated by a quark gluon plasma, will be much more easily stretched and will produce a different gravitational wave signature than a star with a very stiff interior made of normal neutrons that strongly resist deformation. By comparing the signals detected by observatories like LIGO and Virgo with millions of theoretical simulations, physicists can effectively rule out entire families of equations of state, homing in on the true properties of matter at densities that cannot be recreated in any laboratory on Earth. So, why is determining this specific relationship between mass and radius so vitally important? The answer lies in something called the equation of state of ultra-dense matter. This isn't a single equation, but rather a theoretical description of how matter behaves and responds to pressure under these extreme conditions. It is the ultimate physics of the impossible. Different proposed models for the neutron star's core, whether it contains hyperons, pion condensates, or free quarks, all predict different possible relationships between a star's mass and its radius. For example, an equation of state that describes very soft, compressible matter would allow a massive neutron star to be quite small in radius. On the other hand, a stiffer equation of state, where matter strongly resists further compression, would result in a larger radius for the same mass. By collecting precise measurements of mass and radius from many different neutron stars using all these techniques, we are essentially creating an observational scatter plot. Each new data point helps us to rule out theoretical models that don't fit the real-world evidence, narrowing down the possibilities until we uncover the one true equation of state that governs the most extreme matter in the universe. Every measurement, whether from a flickering X-ray burst, a pulsar's timed pulse, or a ripple in spacetime, brings us one step closer to answering one of the most profound questions in all of physics. What happens to matter when it is crushed beyond the limits of atomic nuclei? At the heart of every stellar death, a simple but profound cosmic rulebook dictates the final outcome. This entire dramatic process is governed by two critical numbers, two mass limits that serve as the universe's ultimate gatekeepers, determining whether a dying star becomes a white dwarf, a neutron star, or vanishes entirely into a black hole. The first of these is the Chandrasekhar limit, named for the brilliant astrophysicist Subrahmanyan Chandrasekhar who first theorized it. This limit, approximately 1.4 times the mass of our Sun, represents the maximum possible mass for a white dwarf star. A white dwarf is what remains after a sun-like star exhausts its fuel and gently puffs off its outer layers. It's a dense Earth-sized ember, supported against its own gravity by a quantum mechanical effect called electron degeneracy pressure. Think of it as all the electrons in the star being packed together so tightly that they simply cannot be compressed any further, creating an immense outward force. But this quantum support system has a breaking point. If the white dwarf's mass is at or below the Chandrasekhar limit, it remains stable, slowly cooling over billions of years. However, if it somehow acquires more mass, perhaps by siphoning gas from a binary companion, and pushes over that 1.4 solar mass threshold, electron degeneracy pressure catastrophically fails. The star can no longer support its own weight, and it implodes, triggering a supernova explosion that leaves behind a neutron star. This is where the second, and even more mysterious, cosmic gatekeeper comes into play, the Tolman-Oppenheimer-Volkoff limit, often called the TOV limit. Just as the Chandrasekhar limit defines the maximum for a white dwarf, the TOV limit is the theoretical upper boundary for a neutron star. Once a star's collapsed core exceeds this critical mass, not even the incredible neutron degeneracy pressure, the quantum force that stops protons and electrons from being crushed into neutrons, can hold back the force of gravity. The result is inevitable and total. The entire structure collapses into a singularity, forming a black hole from which not even light can escape. While the Chandrasekhar limit is a relatively firm number, the precise value of the TOV limit is one of the most sought-after prizes in all of modern astrophysics. Current estimates place it somewhere between 2.1 and 2.3 times the mass of our Sun, but that uncertainty is the entire point of the hunt. Pinpointing this number isn't just an academic exercise, it is the key to unlocking the true nature of matter at its absolute breaking point. The reason the TOV limit is not a single, fixed number is that it depends entirely on the neutron star's internal composition, which is governed by its equation of state. As we've explored, we don't know for certain if the core is a superfluid of neutrons, a solid mass of strange quark matter, or a hybrid of different exotic phases. Each of these possibilities has a different stiffness, an equation of state that describes very soft, compressible matter, like a quark gluon plasma, would mean that adding even a small amount of mass causes the star to shrink significantly, resulting in a relatively low maximum mass, perhaps closer to 2.1 solar masses. Conversely, a very stiff equation of state where matter strongly resists compression would allow a neutron star to support a much greater weight against collapse, potentially pushing the TOV limit up to 2.4 or even 2.5 solar masses. So, by simply measuring the mass of the most massive neutron stars we can find, we are directly testing these theoretical models. Every new heavyweight champion we discover acts as a judge, ruthlessly eliminating any theoretical equation of state that predicts a maximum mass lower than what we observe in the real universe. This is why the discovery of neutron stars like PSRJ 0348 plus 0432, with a mass measured at 2.01 solar masses, and the even more massive PSRJ 074 plus 6620, with a mass of about 2.14 solar masses, sent such ripples of excitement through the astrophysics community. These objects aren't just record holders, they are critical boundary markers. Their very existence tells us that the equation of state of ultra-dense matter must be sufficiently stiff to allow for such massive objects to exist without immediately collapsing into black holes. They have already ruled out a host of softer, more compressible models. The ongoing quest is to find even more massive neutron stars, or to find the precise edge where they cease to exist, finally nailing down the exact conditions under which gravity wins its final victory over the fundamental forces that hold matter together. As we push further into the frontiers of how we observe these cosmic powerhouses, we arrive at a revolutionary tool that lets us listen to the very vibrations of spacetime, gravitational waves. For decades, our view of the universe was limited to what we could see with light, from radio waves to gamma rays. But with the advent of gravitational wave observatories, we have gained an entirely new sense, allowing us to hear the cosmos. And neutron stars, particularly when they pair up and spiral together in a final, deadly dance, have become one of the most prolific and informative sources of these cosmic symphonies. When two neutron stars orbit each other, their immense masses churn the fabric of spacetime around them, constantly generating ripples that travel outward at the speed of light. These ripples are gravitational waves, and they carry encoded information about the orbiting bodies, their masses, their distances, and even the internal structure of the stars themselves, offering a direct probe into conditions that light alone could never reveal. The monumental importance of this new window was cemented on August 17, 2017, when the LIGO and Virgo observatories detected a signal that would change astronomy forever. This event, officially named GW170817, was not just another blip in the data. It was the first time a gravitational wave signal was unambiguously traced to the merger of two neutron stars. For about 100 seconds, the twin LIGO detectors in the United States and the Virgo detector in Italy listened as the characteristic chirp of the inspiral grew higher in frequency and louder in amplitude, a telltale sign of two massive objects closing in on each other. The signal culminated in a final, frantic burst as the two stellar corpses collided and merged, likely forming either an incredibly massive neutron star or promptly collapsing into a black hole. This event was a scientific bonanza because, for the first time, the gravitational wave detection triggered a massive follow-up campaign across the electromagnetic spectrum, turning the entire astronomical community into a single, coordinated detective agency. What happened next was an unprecedented global race. The gravitational wave signal provided a rough sky location, and within hours, telescopes all over the world and in space swiveled to that patch of sky. The prize was found less than half a day later, a brand new bright point of light in a galaxy known as NGC 4993, located about 130 million light-years away. This was the kilonova, the brilliant radioactive glow from the debris ejected during the merger. The observations that followed were a feast for scientists. They saw the glow change color from blue to red over days, a signature of the rapid production of heavy elements through a process called rapid neutron capture, or the R process. The data provided the first direct, observational evidence that neutron star mergers are cosmic forges, responsible for creating a significant portion of the universe's heaviest elements, including gold, platinum, and uranium. A single merger like GW170817 can forge hundreds of Earth masses worth of gold and other precious elements, scattering them across the galaxy to one day become part of new solar systems and perhaps even life. But beyond the dazzling firework, the gravitational waves from such an event provide a unique and powerful way to study the neutron stars themselves. The pattern of the ripples during the inspiral phase is exquisitely sensitive to the tidal forces each star exerts on the other. As the stars get closer, their immense gravity stretches them, creating bulges. How easily a neutron star deforms under this influence, a property called its tidal deformability, is a direct window into its internal stiffness or its equation of state. A star with a soft interior, perhaps one with a core of exotic quark matter, will be much more easily stretched and will produce a different gravitational wave signal than a star with a very stiff interior that strongly resists deformation. By comparing the GW170817 signal with millions of theoretical models, physicists were able to place tight constraints on the possible sizes and internal compositions of the merging neutron stars, effectively ruling out many equations of state that were too soft or too stiff. It was like performing a remote ultrasound on the stars from 130 million light-years away, probing the fundamental nature of matter at densities trillions of times greater than water. This single event demonstrated the immense power of multi-messenger astronomy, where information from both gravitational waves and light is combined to form a complete picture of a cosmic event. The gravitational waves told us about the dynamics of the merger and the masses of the objects, while the electromagnetic observations revealed the aftermath and the elemental creation. Together, they confirmed long-standing theories and opened up new avenues of inquiry. The detection of GW170817 was not an endpoint, it was a beginning. It proved that these mergers are relatively common and that our detectors are sensitive enough to find them. As the LIGO, Virgo, and now the CAGRA observatories continue to be upgraded, they will detect more and more of these cosmic collisions, each one providing another data point to refine our understanding of the neutron star equation of state. We are no longer just looking at the universe, we are listening to its most violent and energetic events, and the stories these echoes tell are reshaping our very understanding of matter, gravity, and our cosmic origins. But perhaps the most profound connection between these distant cosmic collisions and our own existence lies in the very atoms that make up our bodies and our world. Every single piece of gold in a wedding ring, every trace of platinum in a catalytic converter, and even the radioactive uranium that provides power, all originated in the most violent events in the universe. These heavy elements are not forged in the gentle furnaces of living stars. They are born in the chaotic aftermath of neutron star mergers through a spectacular process known as rapid neutron capture, or the R process. This is the cosmic alchemy that transforms the ashes of dead stars into the building blocks of planets and life itself, directly linking the fate of those distant, colliding cinders to our own. To understand this incredible process, we first need to appreciate why creating heavy elements is so difficult. Inside ordinary stars, fusion builds elements step by step, slamming nuclei together to make progressively heavier ones. This works beautifully up to iron, but fusing elements beyond iron consumes energy instead of releasing it, so this process simply shuts down in a stable star. To build heavier nuclei like gold, platinum, or uranium, you need a different kind of forge altogether, one that can bombard existing seed nuclei with a tremendous flood of free neutrons in an incredibly dense and energetic environment. This is precisely the condition created in the material ejected when two neutron stars spiral together and finally merge. The collision shreds and flings out tiny fragments of neutron-rich matter, creating a hot, expanding cloud that is absolutely saturated with free neutrons, a perfect cosmic crucible for the R process. In this fleeting, ultra-dense environment, the magic happens at an astonishing speed. Atomic nuclei, like seeds, are bombarded by a veritable blizzard of neutrons. Because the neutron density is so incredibly high, these neutrons are captured by the seed nuclei much faster than the resulting unstable nuclei can undergo radioactive decay. Imagine a snowball rolling down a hill, gathering more and more snow at a rate so fast it never has a chance to melt. In the same way, a nucleus can rapidly swell in size, capturing dozens of neutrons in just a second or two, climbing up the periodic table to form extremely heavy, unstable isotopes. This frantic climb is followed by a period of consolidation, as these overstuffed, unstable nuclei begin to decay back toward stability, transforming neutrons into protons through beta decay. This series of rapid captures and subsequent decays forges entirely new elements, all the way up to the heaviest ones we find on Earth and throughout the cosmos. The significance of this process is staggering. Scientists now estimate that a single neutron star merger can produce an amount of heavy elements equivalent to hundreds of times the mass of the entire Earth. Just one of these cosmic collisions can seed an entire galaxy with the raw materials for rocky planets and, potentially, life. This means that the gold in your jewelry was almost certainly created in a cataclysmic merger that occurred billions of years ago in a galaxy far, far away, long before our own solar system even formed. That material was then scattered across space, eventually mixing with the gas cloud that would collapse to form our Sun and its planetary system. We are, quite literally, made from the stardust of these incredible explosions. Every time we look at a precious metal, we are holding a tangible piece of a cosmic event of almost unimaginable power, a direct artifact from one of the universe's most extreme and creative forces. Even the most reliable cosmic clocks can sometimes behave in unpredictable ways, revealing that beneath their seemingly placid exteriors, neutron stars are churning with incredible internal dynamics. For decades, astronomers have tracked the spins of pulsars, marveling at their atomic clock precision. Their rotational periods can be measured with such fidelity that the slightest deviation, a change of just 1/1,000,000th of a second, is immediately noticeable. It was during such meticulous monitoring that scientists stumbled upon a truly bizarre phenomenon, the pulsar glitch. Imagine listening to a metronome that has ticked with perfect regularity for years, and then, without warning, it suddenly skips a beat and begins ticking slightly faster, forever changing its rhythm. This is precisely what a glitch is: a sudden, tiny, but permanent increase in a pulsar's rotation speed. For an object that is the epitome of cosmic stability, this sudden hiccup is both startling and immensely informative. The increases might sound minuscule, but in the world of precision astrophysics, they are monumental. A typical glitch might cause a pulsar to spin faster by just 1 part in a billion, but given that some of these objects rotate hundreds of times per second, that tiny fractional change represents a significant release of internal energy. In more extreme cases, the change can be as large as 1 part in a million, a veritable earthquake in the star's rotational dynamics. These events are not random. They tend to occur in pulsars that are young and still slowing down relatively quickly from their birth spin. The most famous glitcher is the Vela pulsar, which has exhibited several major glitches over the decades of observation, each one providing a new data point for understanding the frantic activity occurring deep within its solid crust. So, what could possibly cause a city-sized object with the mass of a sun to suddenly speed up its spin? the leading explanation is as fascinating as the glitch itself, and it points directly to the exotic superfluid that is believed to exist in the neutron star's interior. Recall that beneath the solid crust lies an immense ocean of neutrons behaving as a superfluid, a frictionless quantum liquid that can flow without any loss of energy. In a rotating superfluid, quantum mechanics dictates that the flow is organized into trillions upon trillions of microscopic whirlpools called vortices. Normally, in a mature pulsar, the star's solid crust is gradually slowing down due to its emission of radiation and particles. The superfluid core, however, wants to keep spinning at its original, faster rate because of its quantum properties. It's as if the outer shell of the star is breaking while the inner liquid heart is still trying to dash forward. This is where a process called vortex pinning comes into play. The incredibly dense lattice of the neutron star's inner crust is thought to be riddled with imperfections and nuclear structures. The swirling vortices in the superfluid can become physically pinned or anchored to these structures, like a piece of seaweed caught on a coral reef. As long as these vortices remain pinned, the superfluid core is effectively decoupled from the slowing crust. The crust keeps breaking, but the superfluid retains its higher rotational momentum. This creates a growing differential rotation between the two components, building up immense stress, much like winding up a spring. Eventually, the strain becomes too great. The pinned vortices suddenly and catastrophically unpin themselves all at once, transferring a massive amount of angular momentum from the faster spinning superfluid directly to the solid crust. In an instant, the crust receives a sudden rotational kick, and we on Earth observe it as a glitch, a tiny but definitive speed up in the pulsar's spin. The study of these glitches is far more than just cataloging a celestial oddity. It is one of the very few ways we have to directly probe the internal structure and behavior of a neutron star. By analyzing the size and frequency of glitches, scientists can effectively perform remote seismology on these distant objects. The way a glitch unfolds, whether it's a single sudden jump or a series of smaller steps in rapid succession, tells us about the strength of the pinning forces in the crust and the viscosity of the superfluid. It reveals how the different layers of the star are coupled together. A glitch is, in essence, a stethoscope placed against the chest of a cosmic giant, allowing us to listen to the frantic quantum heartbeat raging within. Each event provides a crucial constraint for theoretical models, helping us to understand the properties of superfluidity under conditions of density and pressure that are forever beyond the reach of any laboratory on Earth. Yet surrounding this incredibly solid crust is something almost impossibly delicate, the neutron star's atmosphere. It is a layer of matter so tenuous that if you could hold a cubic centimeter of it, it would contain fewer atoms than the best laboratory vacuum we can create on Earth. This isn't an atmosphere in the terrestrial sense, with swirling weather patterns and a gentle pressure. Instead, it is a vanishingly thin skin of gas, likely only a few centimeters thick, clinging desperately to the surface under the influence of that 100 billion times Earth's gravity. Despite its minimal nature, this atmosphere is our primary window for observing the neutron star's surface directly. It is the source of the thermal X-ray glow we detect, and by dissecting the specific signatures within that light, astronomers can perform a kind of remote spectroscopy, decoding the atmosphere's composition and the brutal physical conditions that define this alien environment. The composition of this gaseous shroud is a subject of intense study and debate. There are two leading possibilities, each telling a very different story about the star's history and current state. The first is a hydrogen atmosphere. If the neutron star is in a binary system and actively accreting material from a companion, that stolen gas is typically hydrogen-rich, providing a fresh, ongoing supply to replenish the atmosphere. The other possibility is an atmosphere dominated by much heavier elements like carbon, oxygen, or even iron. This is more likely for an isolated neutron star that has long since burned off any primordial light elements. In this scenario, the fierce surface gravity, combined with the intense radiation and temperature, can cause a process called gravitational separation. Lighter elements like hydrogen and helium, if they were ever present, can be literally floated away or diffused out of the atmosphere by radiation pressure, leaving behind a purer layer of heavier atoms that have settled onto the surface, much like dense sediment settling at the bottom of a lake. So how do we determine the recipe of an atmosphere on an object millions of light years away? The answer lies in analyzing its spectrum, the detailed breakdown of its light into different energies or colors. When the hot surface and its thin atmosphere emit thermal radiation, the atoms in the atmosphere leave their unique fingerprints on this light. Electrons within the atoms absorb specific, discrete amounts of energy, corresponding to transitions between different energy levels. In an optical star, this creates the dark absorption lines we see in a rainbow spectrum. On a neutron star, however, the environment is so extreme that the spectrum is radically transformed. The primary emission is in X-rays, not visible light, and the fingerprints are not sharp, easily identifiable lines. The immense gravity and powerful magnetic fields warp these atomic signatures into broad, smeared-out features that require sophisticated models to interpret. The surface gravity itself has a profound and measurable effect known as gravitational redshift. As the X-ray photons struggle to climb out of the star's deep gravitational well, they lose energy. This causes their wavelength to shift toward the red end of the spectrum. The amount of this redshift is directly proportional to the star's mass and inversely proportional to its radius. By measuring this subtle shift in the spectrum, astronomers can effectively weigh the star and determine its size from a mind-boggling distance. It's a direct test of general relativity and provides one of the most fundamental measurements in all of astrophysics. Meanwhile, a strong magnetic field adds another layer of complexity and information. It can split the atomic energy levels into multiple components, a phenomenon called the Zeeman effect, creating a pattern of spectral features that is unique to that specific field strength. By fitting observed X-ray spectra to complex theoretical models that account for composition, gravity, and magnetism, scientists can solve for all these variables at once, turning a faint trickle of high-energy photons into a detailed diagnostic report on the state of a stellar corpse. This spectroscopic analysis is a painstaking process, but the rewards are immense. For a neutron star with a strong magnetic field, a magnetar, the atmosphere's spectrum reveals the incredible stresses the field imposes on matter. For a quieter, isolated neutron star, a clean measurement of a heavy element atmosphere confirms our theories about gravitational settling and the long-term evolution of these objects. Every time an X-ray telescope like Chandra or XMM Newton takes a long, careful exposure of a distant neutron star, it is not just collecting light. It is gathering the raw data needed to build a profile of an environment that defies imagination, allowing us to understand the final resting state of matter after it has been processed through the fury of a supernova and compressed into one of the most exotic forms the universe allows. We have explored the bizarre atomic landscape of the crust and the tenuous atmosphere above it, but now we must turn our attention to the most minuscule, yet incredibly powerful surface features imaginable. Even on an object whose gravity strives for absolute perfection, there exist tiny imperfections known as mountains. To call these features mountains, however, requires a complete redefinition of the word. On Earth, Mount Everest rises nearly 5.5 miles above sea level. On a typical neutron star, which is only about 12 miles across, the tallest possible mountain is thought to be no more than a few centimeters high. That's about the thickness of your finger. These are not jagged, towering peaks, but the most subtle of wrinkles on an otherwise almost perfectly smooth sphere, a testament to the fact that even nature's most perfect spheres have their tiny flaws. The reason these mountains are so incredibly small comes down, once again, to the neutron star's phenomenal gravity. The immense pull, 100 billion times stronger than Earth's, ruthlessly crushes any significant irregularity. Any feature that dared to rise more than a few centimeters would be instantly flattened, its material flowing like plastic until the surface was smoothed out to near perfection. The existence of these minuscule mountains at all is a direct result of the incredible strength of the neutron star's crust. Remember, this crust is 1 billion times stronger than steel. It is this phenomenal rigidity that allows it to support these tiny deformations against the star's relentless gravitational pull. The mountains are essentially areas where the crust is under immense strain, likely caused by the star's powerful internal magnetic fields twisting the surface, or perhaps from the stresses of a past starquake that cracked the crust and left a permanent, if tiny, scar. They are not formed by tectonic shifts like on Earth, but by the internal dynamics of the star fighting a desperate, frozen battle against its own gravity. Despite their microscopic size, these mountains have a potentially universe-altering effect. As the neutron star rotates, any deviation from perfect symmetry, any lump or bump, no matter how small, means the star is not a perfectly smooth sphere. A rotating, asymmetric object is the perfect engine for generating continuous gravitational waves. Think of it as a celestial lighthouse, but instead of emitting a beam of light, it's emitting a constant, unwavering hum of ripples in spacetime itself. The more pronounced the mountain and the faster the star spins, the stronger this gravitational wave signal becomes. Unlike the violent, chirping waves from a neutron-star merger, this would be a steady, monotone signal, a single, pure note ringing out across the cosmos for millions of years. Detecting this continuous hum is one of the holy grails of gravitational wave astronomy, and it presents a challenge of a completely different nature. The mergers detected by LIGO and Virgo are loud, brief bursts of energy that stand out clearly against the background noise. A continuous wave signal, by contrast, is incredibly faint and buried deep within the data. It's like trying to hear a single, sustained note from a violin played in the middle of a roaring hurricane. To have any hope of finding it, astronomers must engage in a process called coherent integration, where they essentially combine data over months or even years of observation, looking for that one persistent frequency hidden within the noise. The hunt is on, with dedicated searchers using gravitational wave observatories and even data from radio telescopes, all scanning the sky for this elusive, whispering signal from the spinning hills of distant neutron stars. Finding these gravitational waves would unlock a new and powerful way to study these incredible objects. The amplitude of the continuous wave signal would tell us directly about the size of the mountain, the height of that centimeter-scale deformation. This would provide a direct measurement of the breaking strain of the neutron star crust, telling us exactly how much stress this ultra-dense material can withstand before it cracks or flows. This is a fundamental material property that we cannot replicate in any lab. Furthermore, if a mountain is held up by the star's internal magnetic field, detecting its gravitational waves would allow us to map the field's structure beneath the crust, probing the interior in a way that light alone never could. Each tiny mountain, therefore, is not just a curiosity. It is a probe into the extreme physics of density, rigidity, and magnetism. A small imperfection that could reveal the greatest truths about the limits of matter itself. Now we arrive at one of the most fascinating and speculative roles these distant objects might play, a concept that connects the very small to the very large in an incredible way. Beyond being cosmic lighthouses and element forges, neutron stars could also serve as enormous, natural dark matter detectors. This idea proposes that these ultra-dense objects are not just subjects of study themselves, but could become our most powerful tools for finally detecting the universe's most elusive substance. Dark matter, which makes up about 85% of all the matter in the cosmos, has so far resisted every direct attempt to observe it. It doesn't emit, absorb, or reflect light, revealing its presence only through its gravitational pull on galaxies and galaxy clusters. But if certain theoretical models are correct, a lonely neutron star drifting through the vast, dark halo of a galaxy could be the perfect trap for these phantom particles. The process begins with a simple principle: gravity. A solitary neutron star, especially one that is old and has cooled down significantly, provides an incredibly strong gravitational field. As it travels through its host galaxy, it plows through the vast, diffuse cloud of dark matter that astronomers believe permeates every corner of space. If dark matter consists of theoretical particles called WIMP, or weakly interacting massive particles, they would feel this intense gravitational pull. While these particles barely interact with normal matter, they would be drawn in by the star's gravity, accumulating in its core over millions or even billions of years. Think of it like a cosmic spiderweb. The neutron star's gravity acts as the sticky silk, passively capturing these invisible particles as it moves through the galactic dark matter halo. The incredible density of the star means that once a dark matter particle is pulled in, it has a very high probability of colliding with a neutron or another particle, losing energy and becoming gravitationally bound to the star, sinking right down to its center. This slow, steady accumulation has a potentially observable consequence: heating. An old, isolated neutron star should, according to all standard models of stellar cooling, be very, very cold. After tens of millions of years, its primary heat should be gone, and it should only emit a faint whisper of thermal X-rays. However, if dark matter particles are collecting in its core, they could be providing a new, internal heat source. One of the leading theories suggests that these captured dark matter particles can eventually collide and annihilate with each other, converting their mass directly into pure energy according to Einstein's famous equation, E equals mc squared. This process would deposit a significant amount of heat into the neutron star's core, effectively keeping the star warmer than it has any right to be for its advanced age. It would be like finding a dying ember from a long-extinct campfire that is still surprisingly warm to the touch, suggesting something unseen is fueling it from within. This is where our most powerful X-ray telescopes, like Chandra and XMM Newton, become our dark matter hunting tools. Astronomers would search for precisely these kinds of objects, ancient, isolated neutron stars that are completely alone, with no binary companion to provide accretion heat, and no recent starquakes or magnetic activity to explain a warm temperature. If we were to find such a star millions of years old, yet still glowing with a distinct and unexpected warmth in X-ray light, it would be a monumental discovery. This anomalous heat signature could not be easily explained by any conventional astrophysics. It would point directly to an exotic internal heating mechanism, and the annihilation of accumulated dark matter particles would be a prime and incredibly compelling candidate. It would be an indirect detection, but a profoundly significant one, providing the first tangible clue about the properties and behavior of this mysterious substance that shapes the entire cosmos. The implications of such an observation would reach far beyond simply confirming dark matter's existence. The amount of heating depends directly on the properties of the dark matter particles themselves, such as their mass and how likely they are to interact with normal matter. By carefully measuring the temperature of these anomalously warm neutron stars and comparing it with sophisticated theoretical models, physicists could actually begin to constrain the characteristics of the dark matter particle. It would allow us to rule out entire classes of theoretical particles and guide the search for a definitive direct detection here on Earth. This transforms the neutron star from a passive celestial object into an active billion-year-old physics experiment. It leverages the most extreme conditions in the universe to probe the most elusive substance in the universe, offering a unique and powerful pathway to answering one of the greatest outstanding questions in all of modern science. Of all the celestial objects we've explored, it's hard to imagine a time when neutron stars weren't part of our cosmic vocabulary. But there was indeed a moment when these cosmic lighthouses were entirely unknown, waiting to reveal themselves in a way that would baffle and then revolutionize our understanding of the universe. That moment arrived in 1967, not with a bang, but with a series of persistent, meticulous ticks on a chart recorder. A young graduate student at the University of Cambridge named Jocelyn Bell Burnell was analyzing data from a new radio telescope she had helped build, a sprawling network of wires and poles covering an area the size of 57 tennis courts, designed to study the twinkling of distant quasars. As she pored over the reams of paper output, her keen eye noticed something peculiar. A faint, scruffy signal that appeared night after night, not in a random patch of sky, but always from the same precise location. It was a series of sharp pulses, arriving with a regularity so perfect it seemed almost artificial, ticking away with a period of about 1.337 seconds. This was not the messy, static-filled signal of a quasar. This was a clean, repeating beat, a rhythm echoing out of the void with the unwavering consistency of a metronome. The sheer precision of the signal was so extraordinary that it led the team, for a brief and thrilling period, to entertain a truly fantastic possibility. They half-jokingly labeled the source LGM-1 for Little Green Men. The idea that they might have stumbled upon a beacon constructed by an advanced extraterrestrial civilization was not entirely dismissed out of hand. After all, what natural phenomenon could possibly produce such a perfectly timed signal, a radio broadcast so steady it seemed engineered? The notion captured the imagination of everyone involved, presenting a profound and tantalizing mystery. Was this humanity's first contact with another intelligence, a cosmic hello from the depths of space? The team maintained a necessary skepticism, but the possibility hung in the air, a secret they guarded closely while they worked to gather more data and rule out every conceivable terrestrial or instrumental origin. It was a time of immense excitement and tension, standing on the precipice of a discovery that could fundamentally alter our place in the cosmos. The mystery began to unravel as Jocelyn Bell continued her diligent observations, scanning different parts of the sky with the same instrument. Before long, she found a second source of pulses, this one with a slightly different rhythm. Then she found a third, the probability of 3 separate alien civilizations all deciding to build radio beacons aimed at Earth seemed vanishingly small. The signal was not a message, it was a natural phenomenon, a new type of celestial object. The Little Green Men hypothesis was officially abandoned, and the team turned to the far more challenging task of explaining what in the universe could possibly behave this way. The object was named a pulsar, a portmanteau of pulsating star, and the first one, discovered by Bell, is now catalogued as PSRB 1919+21. The scientific paper announcing the discovery was published in 1968, and it sent shockwaves through the astronomical community, instantly creating an entirely new and frantic field of observational and theoretical research. The true identity of this pulsing object was pieced together through brilliant theoretical work. Astronomers Thomas Gold and Franco Passini, working independently, soon provided the now accepted explanation. A pulsar was a rapidly spinning, highly magnetized neutron star. The concept of a neutron star had been a purely theoretical idea since the 1930s, proposed by Walter Baade and Fritz Zwicky, but no one had ever observed one, and many were skeptical they could even exist. The discovery of the pulsar was the direct observational proof. The model perfectly explained the signals. As the neutron star spins, its powerful magnetic fields act like a colossal cosmic generator, accelerating charged particles that then emit beams of radio waves from the magnetic poles. If those poles are misaligned with the rotation axis, the beams sweep through space like a lighthouse. When a beam crosses our line of sight, we detect a pulse. The incredible regularity of the pulses was simply the rotation period of this city-sized stellar corpse, a clock of unimaginable stability set in motion by a supernova explosion thousands of years earlier. The impact of this discovery cannot be overstated. It was a triumph of careful observation and open-minded scientific inquiry. Jocelyn Bell Burnell's persistence and attention to detail in the face of a mountain of mundane data led to one of the most significant astronomical finds of the 20th century. For the first time, we had direct evidence for the existence of neutron stars, confirming a decades-old prediction and opening a window into the most extreme states of matter in the universe. It validated the link between supernova explosions and these dense remnants and gave astronomers a powerful new tool. Pulsars became natural laboratories for studying general relativity, plasma physics, and the interstellar medium. The field of neutron star astronomy was born from that faint, scruffy signal on a chart recorder, a humble beginning for our journey to understand the universe's most powerful and enigmatic objects, a journey that continues to this day, pushing the very frontiers of physics itself. But beyond their roles as cosmic clocks and gravity labs, certain binary neutron star systems hold a key to one of the most fundamental numbers in all of cosmology, the Hubble constant. This single value describes the current expansion rate of our universe, telling us how fast galaxies are receding from us at any given distance. Pinpointing this number with absolute precision is crucial because it tells us the universe's age, its future, and helps us understand the nature of the dark energy that drives its acceleration. For decades, astronomers have used two primary methods to measure the Hubble constant, but a troubling problem has emerged. These methods don't quite agree. They are in a state of tension, creating one of the most exciting puzzles in modern science. This is where a special class of binary neutron star systems, especially those where both stellar corpses are observable as pulsars, enters the stage, offering a completely independent and exquisitely precise way to measure this critical cosmic parameter. The traditional methods for measuring the Hubble constant create this fascinating dilemma. One approach looks at the very early universe using the detailed map of the cosmic microwave background radiation, the faint afterglow of the Big Bang. By studying the tiny fluctuations in this ancient light, scientists can extrapolate forward to predict what the expansion rate should be today. The other method looks at the relatively recent universe, using a type of star known as a Cepheid, variable as a standard candle, to measure distances to nearby galaxies, and then connecting those to the galaxy's recession speeds. The problem is that the early universe method and the late universe method give slightly different answers for the Hubble constant. It's as if you calculated how fast a car was going by looking at its tire tracks and then got a different answer by timing it between 2-mile markers. This discrepancy, known as the Hubble tension, suggests there might be something missing from our standard model of cosmology, perhaps a new type of particle or a misunderstanding of dark energy. Resolving this requires a third, completely independent way to measure the expansion rate, one that bypasses the entire cosmic distance ladder and its potential pitfalls. This is the monumental role that binary neutron stars are now playing. The method relies on a breathtaking combination of precision timing and gravitational wave physics. Imagine a binary system where both neutron stars are pulsars, flashing their lighthouse beams at us with metronomic regularity. By tracking the slight variations in the arrival times of their pulses as they orbit each other, astronomers can determine the system's orbital parameters with phenomenal accuracy. We can learn the orbital period, the eccentricity, and most importantly, the inclination of the orbit relative to our line of sight. This incredibly detailed orbital map, derived purely from the timing of the radio pulses, gives us a complete three-dimensional understanding of the system's dynamics without ever needing to see it directly. This precise orbital information is the first crucial piece of the puzzle, allowing us to create a perfect model of the binary system's behavior in our own galactic neighborhood. The transformative moment occurs when such a binary system is seen to merge. When these two neutron stars spiral together, they emit a torrent of gravitational waves, ripples in spacetime that we can now detect with observatories like LIGO and Virgo. The gravitational wave signal we receive contains its own unique information. Specifically, the amplitude of the waves tells us the so-called luminosity distance to the source. This is a direct, absolute measurement of how far away the merger happened, calculated purely from the strength of the space-time ripples as they passed by Earth. It's a direct cosmic ruler, independent of any other stars or assumptions. So, from the gravitational wave signal alone, we get a direct readout of the distance to the galaxy hosting the merger. Now, here is where the magic happens and the connection to the Hubble constant is made. After the gravitational wave event, astronomers use traditional telescopes to find the host galaxy of the merger. They then measure the galaxy's redshift, how much its light has been stretched by the expansion of the universe. Redshift is a direct measure of the galaxy's recessional velocity. We now have the two key pieces of information needed to calculate the Hubble constant: the galaxy's velocity from its redshift and its distance from the gravitational wave signal. The Hubble constant is simply the velocity divided by the distance. This method is beautifully direct and sidesteps the entire cosmic distance ladder, relying only on the straightforward physics of gravitational waves and the Doppler effect. The gold standard for this technique was the historic event GW170817, the first binary neutron star merger ever detected. While that system was not a double pulsar, it perfectly demonstrated the principle. The gravitational waves gave a distance of about 130 million light-years, and the identified host galaxy, NGC 4993, had a measured redshift. Combining these gave a valuable, independent measurement of the Hubble constant. However, the future of this technique is even brighter with double pulsar systems. A binary system where both neutron stars are observable pulsars provides that exquisitely precise orbital map before they merge. This means that when they finally do spiral in and create gravitational waves, we will have an even more detailed understanding of the system's orientation, which can refine the distance measurement from the gravitational wave signal to an even greater degree of precision. Each such event acts as a single, perfectly calibrated data point in the grand cosmic graph of expansion. As our gravitational wave detectors become more sensitive and detect more of these mergers, the independent measurement of the Hubble constant will become increasingly precise, helping to resolve the tension between other methods and potentially revealing new physics that governs the expansion of our entire universe. Perhaps the most visually spectacular display a neutron star can produce is the launch of a relativistic jet, a feat that turns these dense objects into the universe's ultimate particle accelerators. In certain X-ray binary systems where a neutron star is actively feeding on a companion, the process of accretion doesn't just create a hot disk of glowing gas. It can also power the formation of two narrow, oppositely directed beams of plasma that shoot out from the system's poles at velocities incredibly close to the speed of light. These aren't gentle streams, they are hypersonic blowtorches, focused and collimated with unbelievable precision, carrying immense energy away from the neutron star and deep into interstellar space. Witnessing such an event is like watching a cosmic blowtorch etch its signature across the galaxy, a temporary but brilliant scar on the face of the cosmos. The engine for this phenomenal display is a complex and powerful alliance between the neutron star's gravity, its rotation, and its magnetic field. It all begins in the superheated accretion disk, that swirling whirlpool of stolen stellar material. As gas spirals inward, it doesn't just fall placidly onto the surface. It becomes magnetized and caught up in the star's immensely powerful magnetic field lines. Think of the magnetic field as a set of rigid, invisible rails that guide the incoming material. The physics happening in the innermost regions of this disk, just before the gas makes its final plunge, are where the magic occurs. Here, powerful magnetic forces and intense radiation pressure can combine to redirect a small fraction of the inflowing material. Instead of falling onto the poles, this material gets funneled, accelerated, and launched outward along the star's rotational axis, perpendicular to the plane of the disk. It's as if the chaotic, inward spiraling traffic of the accretion disk hits a cosmic roundabout that flings a select few vehicles out into intergalactic space at nearly the maximum speed the universe allows. The sheer power required to achieve this is almost beyond comprehension. To accelerate blobs of ionized gas or plasma to such a significant fraction of light speed requires a tremendous release of energy, and that energy comes directly from the gravitational potential of the material falling inward. As gas loses gravitational energy in the intense pull of the neutron star, that energy is converted into the kinetic energy of the jet. In the most extreme systems, the jets can carry away more energy than is actually emitted as light from the entire binary system. What we are seeing is a cosmic balancing act where the star violently ejects a portion of the material it's trying to consume, regulating its own growth and releasing a torrent of energy back into its environment. These jets become a primary way for the system to shed excess angular momentum and energy, acting as a powerful release valve for the violent physics of accretion. Once launched, these relativistic jets do not simply vanish into the darkness. They leave a lasting and detectable mark on their surroundings. As the jet rams into the tenuous gas and dust of the interstellar medium, it creates a spectacular shock wave. The leading edge of the jet plows into this static material, much like a supersonic airplane creates a sonic boom in the air. This collision violently compresses and heats the interstellar gas, causing it to glow brilliantly, particularly in the radio part of the electromagnetic spectrum. Over time, this ongoing interaction can create vast, ballooning structures on either side of the binary system known as radio lobes. These are immense, often symmetrical clouds of energetic particles that can span distances many times larger than our entire solar system. They serve as a fossil record of the jet's activity, a lingering ghost in the interstellar medium that can persist for thousands of years after the jet itself has shut off, allowing astronomers to piece together the history of these cosmic engines long after their most active phase has concluded. For astronomers, these jets and their resulting radio lobes are not just beautiful cosmic sculptures, they are incredibly useful tools. The presence of a powerful, collimated jet is a clear signpost of an active accretion process onto a compact object, helping to distinguish a neutron star system from other celestial phenomena. By studying the size and shape of the radio lobes, scientists can estimate the total energy the jet has deposited into its environment and the duration of its activity. Furthermore, because the jets are moving at relativistic speeds, their light is subject to special effects predicted by Einstein's theory of relativity. If a jet is pointed nearly directly towards us, its emission can be dramatically brightened due to a phenomenon called relativistic beaming, making the system appear much brighter than it would otherwise. This allows us to detect these incredible structures across staggering intergalactic distances, turning them into visible beacons that highlight the most energetic and dynamic interactions occurring in the distant cosmos. While most neutron stars in binary systems engage in a relatively stable dance with their partners, there exists a far more predatory class of celestial object that takes cosmic vampirism to its absolute extreme. These are the sinisterly named Black Widow and Redback pulsars, binary systems where the neutron star isn't just siphoning material from its companion, it is actively, relentlessly, and mercilessly destroying it. The names are a chillingly perfect fit from the natural world, evoking the spiders where the female consumes the male after mating. In these cosmic analogues, a rapidly spinning millisecond pulsar bathes its nearby, low-mass stellar companion in such an intense hail of radiation and particles that it is slowly but surely being evaporated away into nothingness, leaving behind a ghost of a star and a pulsar that may one day be left completely alone. The destructive mechanism at work in these systems is as brutal as it is fascinating. In a typical X-ray binary, the primary danger for the companion star is having its mass stripped away by gravity. But in a black widow or redback system, the pulsar has an even more potent weapon, its pulsar wind. This is not a gentle breeze, but a torrential, magnetized outflow of high-energy particles, electrons and positrons, that streams outward at nearly the speed of light, carrying with it the rotational energy of the rapidly spinning neutron star. This wind creates a powerful pressure that batters the facing side of the companion star, but the true devastation comes from the intense high-energy radiation. The pulsar's beams of gamma rays and X-rays deliver a continuous, searing blast of energy onto a small portion of the star's surface, heating it to the point where material doesn't just flow away, it is blasted off, boiling directly from the surface into space in a process known as ablation. Over millions of years, this relentless erosion can strip a star down to a tiny fraction of its original mass, leaving behind a bizarre planetary mass husk that is being utterly consumed. Astronomers differentiate between the two classes based on the remaining mass of the victim star, which dictates the observable drama of the system. Black widow pulsars represent a later, more advanced stage of destruction. In these systems, the companion star has already been whittled down to an extremely low mass, often less than 5% the mass of our Sun, or even just the mass of a large planet like Jupiter. This tiny, doomed object is so thoroughly cooked by the pulsar's radiation that it is often puffed up and distorted, stretched into a teardrop shape by the gravitational pull of its predator. Because the star is so small and faint, these systems are often discovered when astronomers detect the regular pulses from the pulsar, only to notice that the signal periodically vanishes. This eclipsing happens when the tenuous, evaporated material that has been blown off the star forms a vast, diffuse cloud that envelops the entire binary system. As the pulsar moves behind this shroud of its own making, its radio waves are scattered and absorbed, causing the telltale eclipse that reveals the presence of the stellar corpse being eaten alive. Redback pulsars, named for another genus of cannibalistic spider, are an earlier and even more volatile stage in this process. Here, the companion star is still somewhat more substantial, typically holding between 10 and 50% of the Sun's mass. This greater mass means the star can still hold itself together more effectively, leading to a different and spectacular set of phenomena. The intense heating from the pulsar doesn't just ablate the star, it can cause the side facing the pulsar to become tremendously bloated and hot, creating a massive temperature difference across the star. This can drive powerful, turbulent flows of material, and the system often displays much more violent and variable behavior. Redbacks are notorious for exhibiting intense flares of radio and X-ray emission, likely due to material from the companion star occasionally managing to breach the pulsar wind and crash down onto the neutron star's surface in unpredictable surges. They are chaotic, actively feeding systems, showing us the destruction in progress, whereas black widows show us the near-finished result. Studying these cosmic predators provides far more than just a morbid fascination. They are unparalleled natural laboratories for understanding some of the most elusive physics in the universe. The pulsar wind, which is the very instrument of destruction, is a phenomenon that is incredibly difficult to study in isolation. In black widow and redback systems, the companion star acts as a natural probe, interacting with the wind and allowing us to measure its properties. By observing how the pulsar's signal changes as it passes through the cloud of ablated material, scientists can map the density, structure, and magnetic properties of this hyper-energetic wind. Furthermore, these systems offer a unique window into binary evolution. They demonstrate one of the possible endpoints for a pair of stars, showing how a neutron star can effectively recycle itself by accreting mass and being spun up to millisecond periods, only to then turn on its benefactor and destroy it. This complete narrative arc, from stable binary to cosmic cannibalism, helps astronomers refine their models of how stellar systems change over billions of years, revealing the often violent dynamics that govern the lives and deaths of stars locked in a gravitational embrace. Now, let's take a moment to truly listen to the cosmos. While space is a vacuum where no sound can travel in the conventional sense, the rhythmic radio pulses from pulsars can be translated into sounds we can hear, and the results are both eerie and mesmerizing. Imagine converting the precise, steady beat of a cosmic lighthouse into an audible ticking. Scientists do this by taking the radio wave data collected by massive dishes like the Arecibo Observatory or the Very Large Array and simply mapping the arrival time of each pulse to a click or a tone. What you hear is not an artist's interpretation. It is a direct sonification of the data, a real-time playback of the neutron star's rotation. Listening to the rapid-fire ticking of a millisecond pulsar, for instance, is like hearing a hyperactive cosmic metronome set to an impossible speed, each click representing a full rotation of a city-sized object hundreds of times every second. In contrast, the slower, more deliberate beat of an older pulsar sounds like a vast, echoing heartbeat from the void, a solemn and patient rhythm marking the passage of deep cosmic time. These sounds transform these distant points of light from abstract concepts into tangible, almost living entities, giving them a voice that speaks across the light years. The specific rhythm and pattern of these cosmic sounds are a treasure trove of information, a complex code that astronomers have learned to decipher. The most fundamental property is the period, the time between one pulse and the next. This is the star's rotation rate, a direct measurement of its spin. A pulsar that ticks every few milliseconds is a young, energetic powerhouse, while one that clicks only once every few seconds is a venerable old timer, its spin gradually winding down over millions of years due to energy loss from its magnetic fields and particle winds. But the story doesn't end with a simple, steady beat. Sometimes astronomers detect subtle changes in the rhythm. A gradual, steady increase in the ticking rate can signal that the pulsar is being spun up by accreting material from a binary companion, in the process of being recycled into a millisecond pulsar. Conversely, a sudden, tiny glitch, a minuscule skip and permanent speed up in the rhythm betrays a dramatic starquake or a sudden unpinning of vortices in the superfluid interior, an event that shakes the entire star and changes its rotation in an instant. Beyond the spin itself, the detailed shape of each individual pulse holds clues to the pulsar's magnetic personality. The lighthouse beam isn't necessarily a simple, uniform flash. As it sweeps past us, the intensity and polarization of the radio waves can vary, creating a unique pulse profile for each pulsar, its audiological fingerprint. Some pulses are sharp and single, while others are broad and complex, with multiple peaks and valleys within a single rotation. This intricate structure is shaped by the geometry of the pulsar's magnetic field and the precise location within that magnetic field where the radio waves are generated. By meticulously analyzing the shape of these pulses, scientists can effectively map the otherwise invisible magnetic field lines, understanding their strength and configuration around the star's poles. It's like listening to the echo in a cathedral to determine its shape. The nuances in the sound reveal the structure of the environment that created it. Perhaps one of the most thrilling applications of this precise pulsar timing is the hunt for unseen worlds. If a pulsar has a planetary system, the planets will exert a tiny but measurable gravitational tug on the neutron star, causing it to wobble slightly in space. This minuscule wobble affects the distance the radio pulses have to travel to reach Earth. As the pulsar moves slightly toward us, the pulses arrive just a fraction of a second earlier. As it moves away, they arrive slightly later. This creates a predictable, repeating pattern in the timing of the pulses, a rhythmic deviation from perfect regularity. It was through this exact method that the very first exoplanets ever confirmed were discovered in 1992, orbiting the pulsar PSRB 1257+12. The tiny, systematic variations in its clockwork tick revealed the presence of 3 terrestrial worlds, survivors of the apocalyptic supernova that created their neutron star parent, or perhaps planets that formed from the ashes of that explosion. By listening for these delicate timing anomalies, astronomers can detect the gravitational fingerprint of these dark, alien worlds, expanding our understanding of where planetary systems can exist and what forms they can take in the most extreme environments the universe has to offer. Yet one of the most astonishing chapters in the story of these cosmic powerhouses arrived when we discovered they are not always alone in the void. Imagine a world where the sun in the sky is not a gentle, warm ball of light, but a rapidly spinning, city-sized cinder that floods the landscape with lethal X-rays and gamma rays, a sun that blinks on and off hundreds of times every second, casting the world into a strobe-light reality of searing radiation and profound darkness. This is not science fiction. This is the reality for planets orbiting pulsars, some of the most hostile and bizarre worlds imaginable. The discovery of these planets was itself a monumental surprise, one that fundamentally rewrote the textbooks on planetary science. For decades, the search for worlds beyond our solar system was a field of speculation with no confirmed discoveries. Then, in the unlikeliest of places, the answer finally came. The very first extrasolar planets ever confirmed were not found around a calm, sun-like star, but in a graveyard orbiting the millisecond pulsar PSRB 1257+12. The discovery was a masterpiece of precision and deduction, made by astronomer Alexander Wolskson in the early 1990s. He wasn't looking for planets, he was meticulously tracking the clockwork radio pulses from this distant stellar corpse. What he found were tiny but perfectly regular anomalies in the pulse arrival times. The pulses would arrive slightly early for a while, then slightly late in a repeating pattern. This was the telltale signature of a gravitational dance. The pulsar itself was being gently tugged back and forth by the subtle gravitational pull of unseen orbiting bodies. Through painstaking analysis, Wolskson revealed not one, but 3 worlds in this system, with the innermost one being not much larger than our own moon, and the outer ones roughly 4 times the mass of Earth. This was a revelation. It proved that planets could exist in the most violent of environments, surviving the supernova explosion that created their parent pulsar, or perhaps even forming from the ashes of that very cataclysm. It shattered the assumption that planets could only form in the peaceful nurseries around young stars, opening up an entirely new and unexpected frontier in the search for other worlds. The environment on such a world is almost incomprehensibly harsh. These planets are perpetually bathed in an unrelenting torrent of high-energy radiation from their pulsar parent. The pulsar wind, a hurricane of energetic particles, and the beams of X-rays and gamma rays would continuously scour the surface, making the survival of any atmosphere, let alone life as we know it, virtually impossible. The surface of these worlds would be a sterile, blasted landscape, likely heated to incandescent temperatures on the side facing the pulsar. Furthermore, the rhythmic nature of the pulsar's emission creates a bizarre day-night cycle. As the planet rotates, it would be cyclically exposed to the full fury of the pulsar beam, followed by a period of relative darkness, though the background radiation levels would still be lethal. This is not a gentle cycle of sunlight and shadow, but a brutal, pulsing onslaught of energy that would strip away any complex molecules and fry any potential biological material. These are not candidates for habitable worlds. They are case studies in planetary survival under the most extreme conditions the universe can devise. The very existence of these planets presents a profound puzzle. How did they get there? How can a planetary system form from the utter devastation of a supernova explosion that should have vaporized any pre-existing world? Astronomers have developed two leading theories, each as dramatic as the other. The first is a story of cosmic survival against all odds. It's possible that these planets are the scorched and barren remnants of a system that existed before the supernova. In this scenario, the original star had a family of gas giant planets in wide orbits. When the star exploded, the inner planets would have been completely vaporized, but a distant gas giant much farther out might have just barely survived the blast. The supernova would have stripped away its gaseous envelope, leaving behind a rocky or metallic core that continued to orbit the newly born pulsar. This surviving world would be a ghost, a planetary remnant from a system that no longer exists. The second theory is even more extraordinary, suggesting that these planets are not survivors but phoenixes, born from the ashes of the dead star itself. In the chaotic aftermath of a supernova, a vast amount of material is ejected into space. If a significant portion of this debris falls back toward the newborn neutron star, it could form a disk of material around it, a second-generation accretion disk made of metal-rich gas and dust. Within this disk, the same basic processes that form planets around young stars could take place. Dust grains would clump together, building up into planetesimals, which would then collide and merge to form full-fledged planets. In this view, a pulsar planet is a brand new world, forged in the fury of a stellar death. A world built not from the primordial elements of a stellar nursery, but from the heavy elements like iron, gold, and uranium freshly cooked in the supernova itself. This makes these worlds incredibly metal-rich, perhaps even possessing cores of solid diamond or other exotic crystalline structures formed under immense pressure, truly alien landscapes born from the most violent of origins. Tracking the gradual dimming of these cosmic embers over millions of years gives us one of our most powerful tools for peering inside them, the cooling curve. Just as a blacksmith can tell a lot about a piece of hot metal by watching how long it takes to glow red and then fade to black, astronomers can learn profound secrets by charting how a neutron star's temperature drops over its immense lifetime. This isn't done with a simple thermometer, of course. By carefully analyzing the star's thermal X-ray emission with observatories like Chandra, scientists can effectively take its temperature from billions of light years away. When they plot this temperature against the star's estimated age, they create a cooling curve, a graph that tells the life story of the star's internal heat, a story written in the language of fading X-rays. This curve is far from a simple, smooth decline. Its specific shape, its dips and plateaus, acts as a direct window into the frantic and exotic physics raging deep within the stellar core. The journey of a neutron star's heat begins in unimaginable violence. At birth, its surface is a searing 1 million degrees Celsius, a residual fire from the supernova's fury. For the first 10,000 years or so, the primary mechanism for shedding this heat is the emission of neutrinos. These ghostly particles, created in vast numbers deep within the ultra-dense core, have a remarkable ability to stream directly through the solid crust and out into space, carrying immense amounts of thermal energy with them almost unimpeded. This neutrino cooling is an incredibly efficient refrigeration process, causing the star's temperature to plummet dramatically during its youth. However, the efficiency of this process depends critically on what is actually inside the star. If the core is composed of normal neutrons, the cooling will follow one predicted path. But if the pressure has crushed matter into more exotic states, like a soup of free quarks, the neutrino production can become exponentially more efficient. A star with such an exotic core would cool much faster than standard models predict. Its temperature dropping like a stone as its internal furnace is quenched by a flood of escaping neutrinos. After this initial rapid cooling phase, a slower, more gradual process takes over. Once the star is around 1 million years old, the dominant cooling mechanism shifts from internal neutrino emission to simple photon radiation from the surface. The star's outer layers, still glowing fiercely in X-rays, now radiate their remaining heat directly into the void. This phase is like watching a hot coal slowly fade in a cold room. The rate of cooling during this stage is like a cosmic speed limit for heat loss, and it is governed by the star's composition. A neutron star with a light element atmosphere, perhaps replenished by a binary companion, will cool at a different rate than one with a heavy element atmosphere of iron and carbon. The light elements are more transparent, allowing heat to escape more easily, while heavier elements act like a bit of a blanket, slowing the cooling process. By measuring the temperature of middle-aged neutron stars and comparing them to these detailed models, astronomers can infer the composition of their atmospheres, adding another piece to the puzzle. Perhaps the most exciting aspect of these cooling curves is their power to reveal unexpected phenomena. When astronomers find a neutron star that is significantly colder than its predicted age would suggest, it's a major event. This anomalous cooling is a clear signpost that something beyond standard physics is at work, efficiently sapping heat from the star's interior. As we discussed, one compelling explanation is the presence of dark matter particles accumulating and annihilating in the core, providing a secret energy sink. Another possibility involves exotic particles beyond the standard model of physics, such as actions, which could also carry away energy with high efficiency. Each of these scenarios would leave a unique fingerprint on the cooling curve, allowing theorists to test their models against real observational data. The cooling curve thus transforms the neutron star from a distant object into a dynamic laboratory report. Its steadily declining temperature, a direct measurement of the most extreme and elusive physical processes in the universe, offering insights that are simply impossible to gain in any terrestrial experiment. But for all their mind-bending power, the magnetic fields of a neutron star are not a permanent, unchanging fixture of the cosmos. Like the star itself, they evolve over time, gradually fading in a process that can fundamentally alter the star's identity and its impact on the surrounding space. This slow decay is one of the key factors that dictates the long-term life cycle of these objects, transforming a furious, young magnetar into a quieter, more stable pulsar over millions of years. The primary engine driving this magnetic decay is the simple, relentless reality of electrical resistance. While we often picture a neutron star's magnetic field as a static structure, it is actually generated and sustained by incredibly complex electrical currents flowing within the star's super-dense interior, through both the crust and the outer layers of the core. These currents aren't flowing through perfect superconductors. They encounter resistance, and over immense timescales, this resistance causes the currents to slowly dissipate their energy, weakening the overall magnetic field they produce. This isn't a rapid shutdown, but a gradual dimming of the star's magnetic personality. The rate of decay is heavily influenced by the star's internal composition and temperature. In a hot, young neutron star, the interior is more fluid and the electrical resistance is lower, which can actually allow the magnetic field to persist for a longer time. But as the star cools over hundreds of thousands of years, the crust becomes more rigid and the conditions for maintaining those powerful currents become less favorable. The decay is often modeled as an exponential process, meaning the field strength drops very rapidly at first, and then the decline slows to a more gradual crawl over millions of years. For a typical pulsar, the magnetic field might be halved over a timescale of a few million years. For the most extreme magnetars, this initial decay can be even more dramatic, as their immense fields contain tremendous energy that is ripe for dissipation, often through the violent starquakes and giant flares that literally shake the energy out of the magnetic field structure, accelerating its decline. This magnetic fading has a profound effect on the star's observable behavior and its very classification. Consider a magnetar born with a magnetic field 1,000 trillion times stronger than Earth. For the first 10,000 years of its life, it is a tempestuous object racked by starquakes and punctuating the galaxy with brilliant flashes of gamma rays. But as its field decays by a factor of 10 or 100, it crosses a critical threshold. It no longer possesses the magnetic energy to power such catastrophic eruptions. Its crust settles and the starquake activity subsides. What was once a terrifying magnetar has now transitioned into a much more ordinary, though still powerful, rotation-powered pulsar. Its primary energy source is no longer its twisting, decaying magnetic field, but the gradual slowing of its rotation. It has entered a new, more stable phase of its existence, trading its youthful volatility for a long, predictable life as a cosmic lighthouse. This evolutionary path helps explain why we see so few magnetars compared to ordinary pulsars. Their intensely magnetic phase is a relatively brief, dramatic adolescence in the multi-million-year life of a neutron star. The consequences of this magnetic decay extend far beyond the star itself, directly influencing how it interacts with its cosmic environment. A pulsar's powerful wind of particles is driven by its rapid rotation, but it is channeled and accelerated by its magnetic field. As that field weakens, the wind also changes character. It may become less collimated and less energetic, reducing the pressure it exerts on the surrounding interstellar medium. For a neutron star in a binary system, a decaying magnetic field can alter the very dynamics of accretion. A stronger field acts like a shield, preventing material from the companion star from reaching the surface until it is funneled onto the magnetic poles. But as the field weakens, this magnetic barrier diminishes, allowing accreting gas to flow more directly onto the star. This can change the pattern of X-ray emission and potentially even affect how efficiently the neutron star can be recycled and spun up to millisecond periods. The fading magnetosphere literally opens the door for a different kind of relationship with its stellar companion, reshaping the binary system's evolution over cosmic time. But for all their predictable rhythms and gradual evolution, neutron stars are also capable of unleashing some of the most sudden and inexplicable blasts of energy in the entire cosmos. Imagine a flash of radio light so powerful that it releases more energy in a single millisecond than our Sun emits over 80 days, a burst that arrives without warning from the deep voids between galaxies. For years, these events, known as fast radio bursts or FRBs, were one of astronomy's most perplexing puzzles. They were so brief and seemingly random that many scientists wondered if they were even real, or perhaps just glitches in our terrestrial equipment. The breakthrough came when we discovered that some of these titanic, intergalactic explosions were actually originating from our own cosmic backyard. And the culprit was a type of neutron star we are already familiar with, the magnetar. This connection has turned one of the greatest mysteries in modern science into one of the most exciting frontiers, directly linking the bizarre physics of these ultra-dense objects to brilliant flashes that can be seen across the universe. The story of this revelation begins with a specific event in our own galaxy. On April 28, 2020, multiple space-based observatories, including NASA's Swift and Fermi telescopes, detected a tremendous blast of X-rays and gamma rays from a known magnetar called SGR 1935 plus 215, located about 30,000 light-years away. This in itself wasn't entirely unusual for a magnetar, as they are prone to starquakes and smaller flares, but what happened next was unprecedented. At the exact same moment, two radio telescopes on Earth, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, and the Survey for Transient Astronomical Radio Emission 2, or STARE-2, detected an incredibly intense, millisecond-long burst of radio waves coming from the exact same direction. This was a fast radio burst, and it was unambiguously linked to a magnetar right here in the Milky Way. For the first time, we had a smoking gun. This single observation proved that at least some FRBs are generated by these incredibly magnetic neutron stars, finally giving astronomers a solid starting point to unravel the broader mystery. So, how does a magnetar produce such a staggering flash of energy? The leading theory involves a truly apocalyptic event on or near the star's surface, a colossal starquake. Remember, a magnetar's crust is under unimaginable strain from the twisted, evolving magnetic field locked inside. This crust is 1 billion times stronger than steel, but even it has its breaking point. When the stress becomes too great, it fractures. This isn't a gentle crack, it's a rupture that shakes the entire star, releasing more energy than a magnitude 23 earthquake. This sudden, violent rearrangement of the crust causes the magnetic field lines to snap and reconfigure in a process called magnetic reconnection. Think of it as a cosmic-scale short circuit. The immense magnetic energy stored in the field is converted almost instantaneously into a blast of radiation and a torrent of charged particles. This explosion creates a shock wave that plows through the magnetar's own surrounding environment. The cloud of particles previously ejected from its surface, known as its magnetosphere. It is the interaction between this shock wave and the magnetosphere that is thought to generate the brilliant, coherent flash of radio waves we detect as an FRB. In a mere thousandth of a second, a quake on a city-sized object 20,000 light-years away can announce itself with the power of 500 million suns. While the galactic FRB confirmed magnetars as a source, the mystery is far from completely solved. The vast majority of fast radio bursts we detect are not from within our own galaxy. They are extragalactic, originating from sources billions of light-years away. This raises a critical question. Are all FRBs created by magnetars, or are there multiple cosmic engines capable of producing these fleeting flashes? Some of the most intriguing FRBs are the ones that repeat. Unlike the one-off bursts, these repeating sources flicker on and off multiple times, sometimes in a predictable pattern and sometimes at random. This behavior is difficult to explain with a simple, one-time starquake model. It suggests a system that can store and release energy repeatedly, perhaps involving a magnetar in a binary system where the pull of a companion star triggers periodic avalanches on the neutron star's crust. Another possibility is a hyperactive young magnetar, still in its most volatile phase, experiencing a continuous series of major crustal fractures as its magnetic field settles into a stable configuration. Each repeating burst gives astronomers another chance to study the source, to triangulate its home galaxy, and to understand the conditions that lead to such prolific and powerful outbursts. The immense distances of these extragalactic FRBs are not just a hurdle, they are also an opportunity, because these radio waves travel for billions of years across an expanding universe filled with tenuous gas and magnetic fields. They carry an imprint of their long journey. The various wavelengths that make up the burst get slightly spread out as they travel, a phenomenon known as dispersion. By measuring how much a burst has been dispersed, astronomers can estimate the total amount of ionized material it has passed through, providing a unique way to weigh the otherwise invisible normal matter that exists in the vast spaces between galaxies. This turns each FRB into a cosmic tool, a backlight that illuminates the fabric of the cosmos itself. The ongoing quest now involves a global network of radio telescopes working in concert. When a burst is detected, these telescopes quickly slew to its location, seeking to identify the host galaxy. By combining the FRB's dispersion measure with the known distance to its host galaxy, scientists can create a census of the universe's missing matter, helping to solve another long-standing cosmological puzzle. These brilliant, mysterious flashes, born from the magnetic fury of distant neutron stars, are thus more than just spectacular explosions. They are becoming essential probes for mapping the large-scale structure of our universe. We can now turn to one of the most elegant and precise validations of Einstein's theory of general relativity, a test that sounds like pure science fiction but is carried out routinely by astronomers using these cosmic clocks. This involves a subtle but measurable effect called the Shapiro time delay, named after the physicist Erwin Shapiro, who first proposed it in the 1960s. The concept revolves around a simple yet profound principle from general relativity, that matter and energy warp the fabric of spacetime, and that light or any radiation must follow this curved geometry. It's the idea that gravity doesn't just pull on things, it bends the very stage upon which everything plays out. When a pulse of radio waves from a distant pulsar travels across a binary system, its path takes it through the gravitational well of the companion star. According to Einstein, that pulse isn't traveling in a perfectly straight line. It's navigating a curved pathway, and that extra curved distance takes just a little bit more time to traverse than if the spacetime were perfectly flat. It's a tiny, almost imperceptible delay in the arrival time of the pulsar's otherwise metronomic tick. To understand this, picture a binary system with a pulsar and a white dwarf locked in a mutual orbit. From our vantage point on Earth, there will be points in the orbit when the signal from the pulsar on its way to us must pass very close to its companion. As the radio waves skim through this region of warped spacetime, they are effectively forced to take a scenic route. The pulse is delayed by a minuscule amount, often just millionths of a second, but for pulsar timing, that's an eternity. This delay is not constant. It varies predictably as the two stars orbit each other. The effect is at its maximum when the pulsar is located directly behind its companion from our point of view, a configuration known as superior conjunction. At that precise orbital phase, the radio waves are passing through the deepest part of the companion's gravitational field, experiencing the strongest curvature and thus the greatest delay. It's as if the signal is struggling to climb out of a gravitational valley, and that struggle makes it arrive at our telescopes a fraction of a second late. The magic of this effect is that it provides a direct quantitative test of general relativity's predictions. By meticulously tracking the arrival times of thousands of pulses over many orbits, astronomers can build up an exquisitely detailed map of these periodic delays. They then compare this observed pattern with the precise delay curve predicted by Einstein's equations. In system after system, the observations have matched the theory with astonishing fidelity. The level of agreement is often breathtaking, reaching a precision of better than 0.0001% in some of the best measured systems. This isn't just a rough confirmation, it's a stringent, repeatable laboratory experiment on a cosmic scale. It tells us that Einstein's description of gravity as the curvature of spacetime is not just a beautiful abstraction, but an accurate map of how mass and energy truly shape the universe around them. One of the most famous systems for this kind of investigation is the double pulsar, known officially as PSR J07373039A and B. This is a truly remarkable laboratory because it contains not one, but two active pulsars, each beaming its own set of clock-like signals at us. This allows for an incredibly rich set of relativistic measurements. The Shapiro delay in this system has been measured with phenomenal precision, providing one of the most stringent tests ever conducted. But the power of this method goes beyond just testing the theory. It allows us to actually weigh the stars in the system with incredible accuracy. The shape and depth of the Shapiro delay curve depend directly on the mass of the companion star that is warping the spacetime. By fitting the observed delay to the theoretical model, astronomers can solve for that mass. In the double pulsar system, the masses of both neutron stars have been determined through this and other relativistic effects to an accuracy of better than 1 part in 10,000, a level of precision that is simply unattainable by any other means in astronomy. This relentless verification of general relativity in the extreme gravitational fields of binary pulsars has profound implications. It confirms that the theory holds up even in environments far more severe than our solar system, where it was first tested. Every time a pulsar signal is measured to be delayed by exactly the amount Einstein predicted, it rules out alternative theories of gravity that propose slightly different ways that mass could curve spacetime. In a sense, these distant spinning stellar corpses act as our arbiters, judging which physical theories correctly describe the universe. They provide a clean, controlled environment, free from the messy complications of atmospheric distortion or human error, allowing us to probe the fundamental laws of physics with a clarity that is both humbling and inspiring. The persistent, rhythmic ticking from these binaries is more than just a signal. It is a continuous whisper from the cosmos, affirming that we are on the right track in our quest to understand the deepest workings of reality. But to fully appreciate the energy locked within a neutron star, we need to listen to the very ground shaking beneath our feet, or rather, the crust shaking beneath an unimaginable gravity. Welcome to the field of neutron star seismology, the study of starquakes. On Earth, an earthquake is a violent release of stress built up between tectonic plates. On a neutron star, a starquake is the catastrophic release of stress built up in a crust 1 billion times stronger than steel, creating a seismic event of literally cosmic proportions. The forces at play are not moving continents, but the star's own incredible magnetic fields and its gradual slowdown in spin. The neutron star's crust is not a static shell, it's a rigid lattice under immense evolving strain. As the star spins down over millennia, its crust must subtly contract. Meanwhile, the internal magnetic fields, which are frozen into the superfluid core, are constantly evolving and twisting. These two processes place the crust under unbelievable stress, and like any solid under too much pressure, it eventually fractures. When it does, the results make our most powerful earthquakes look like barely perceptible tremors. The scale of energy released in a starquake is almost beyond human comprehension. A magnitude 10 earthquake, the theoretical maximum for our planet, would release roughly the energy equivalent of detonating 1.4 trillion tons of TNT. A single, typical starquake on a magnetar can release more energy than that in a fraction of a second. These events can be billions of times more powerful than the largest earthquake ever recorded. The crust, which may be only a kilometer thick, suddenly shifts by mere centimeters, but in doing so, it unlocks a colossal amount of pent-up magnetic and gravitational energy. This energy floods out from the star not as ground shaking, but as a brilliant, ephemeral flash of hard X-rays and gamma rays. For a brief instant, the star can become one of the brightest objects in the entire gamma-ray sky, outshining entire galaxies in this high-energy band before fading back into obscurity over the following minutes. It's a stark and violent reminder that beneath that seemingly placid, spinning exterior rages an interior of unimaginable forces. These crustal rearrangements have a direct and measurable impact on the star itself. They can suddenly make it spin faster. This phenomenon, known as a pulsar glitch, was one of the most baffling discoveries in early pulsar astronomy. Astronomers would be tracking the incredibly regular spin of a pulsar, watching it slow down at a steady, predictable rate, and then, without warning, its rotation would suddenly jump, spinning up by a tiny but permanent fraction. It was as if a spinning ice skater, gradually slowing down, suddenly and inexplicably pulled their arms in tighter for an instant, causing a rapid speed up. The leading explanation for this is intimately tied to the star's internal structure. The crust is coupled to a superfluid ocean of neutrons in the interior. This superfluid, having zero viscosity, wants to keep spinning at a constant rate while the crust is slowing down. The vortices in this superfluid can become pinned to the crust's crystalline structure, creating a growing differential rotation. When a starquake occurs and the crust suddenly cracks and shifts, it can unpin vast numbers of these vortices all at once, transferring a massive amount of angular momentum from the faster spinning superfluid directly to the solid crust. The entire star gets a sudden, tiny kick in its rotation, which we observe as a glitch in its otherwise perfect timing. Nowhere are starquakes more dramatic and consequential than on magnetars, the magnetic superstars of the cosmos. For a magnetar, the primary source of stress is its own apocalyptic magnetic field. These fields are so strong that they are physically trying to tear the star apart, exerting a strain on the crust that is 1,000,000 times more powerful than the gravitational binding force holding it together. The crust is in a perpetual state of being twisted and stressed, like a rubber band stretched to its absolute limit. It's a losing battle for the crust. It simply cannot withstand such forces indefinitely. When it finally gives way, the resulting starquake is not just a small adjustment. It can be a global-scale event that rearranges the star's magnetic field in a process called magnetic reconnection. This is where the true power is unleashed. The energy released is not just from the cracking crust itself, but from the catastrophic conversion of magnetic energy into radiation and particle acceleration. This is the engine behind the magnetar's most fearsome outburst, the giant flare. A giant flare begins with an intense, short spike of gamma rays that, for a fraction of a second, can outshine every other gamma ray source in the universe combined. This is followed by a periodic tail of X-rays that pulses with the star's rotation, a clear sign that the event was anchored to the star's surface. We've witnessed a handful of these from magnetars in our own galaxy, events so powerful they noticeably affected Earth's upper atmosphere from tens of thousands of light years away, demonstrating that the tremors on these distant, ultra-dense worlds can indeed reach out and touch us across the gulf of space. Now we arrive at a fundamental cosmic speed limit, a boundary set not by engineering but by the immutable laws of physics themselves. Every neutron star, no matter how massive or powerful, faces an ultimate constraint on how fast it can spin before it literally flies apart. This is known as the breakup limit, a critical threshold where the outward pushing centrifugal force generated by the star's rotation finally overcomes the immense inward pull of its own gravity. Imagine spinning a water balloon faster and faster. Eventually, the rubber can't hold it together and it bursts. For a neutron star, the principle is the same, though the forces involved are astronomically more extreme. The balance is incredibly delicate, dictated by the star's mass and radius. A more massive, more compact star, with its correspondingly stronger gravity, can theoretically spin faster without disintegrating than a less massive, more bloated one. This makes the maximum spin rate a direct probe into the star's internal density and stiffness, offering a unique window into the very equation of state that governs matter at its most extreme. The current undisputed champion of cosmic rotation, the fastest spinning neutron star ever observed, is a celestial dynamo known as pulsar J1748-2446 AD, located in the globular cluster Terzan 5. This object is spinning at a mind-numbing 716 times per second. To put that almost incomprehensible speed into perspective, its surface at the equator is whipping around at approximately 1/4 the speed of light. In the time it takes you to blink, this city-sized object has completed over 40 full rotations. The discovery of such a rapid spinner was a major surprise that pushed the boundaries of what we thought was possible. It tells a compelling story about the star's history. It is almost certainly a recycled pulsar that has been spun up to this phenomenal velocity over millions of years by siphoning mass and angular momentum from a binary companion star. The process acts like a cosmic potter's wheel, with the infalling gas transferring its spin to the neutron star, accelerating it to velocities that approach the absolute physical limit set by gravity itself. What does such a phenomenal spin rate reveal about the star's hidden interior? The answer lies in how the star responds to this incredible centrifugal force. As the star spins, it experiences a force trying to flatten it, much like a pizza chef spinning dough to form a disc. The faster it spins, the more oblate or squashed it becomes. The precise amount of this deformation, however, depends critically on the stiffness of the neutron star's interior. If the core is composed of very soft, compressible matter like a quark-gluon plasma, the star will deform more easily under the centrifugal force. It will become more oblate at a given spin rate, and its maximum possible speed before breaking apart would be relatively lower. Conversely, if the star has a very stiff interior, where matter strongly resists being compressed or deformed, it will maintain a more spherical shape even at high rotations, allowing it to reach a much higher breakup speed. The simple existence of pulsar J1748-2446 AD, spinning at 716 times per second, immediately rules out entire families of theoretical models that are too soft, as they would have predicted the star flying apart long before it reached such a velocity. Its very stability is a powerful argument for a sufficiently stiff equation of state in its core. This frantic rotation also has fascinating implications for the star's gravitational field. A perfectly spherical object produces a simple, smooth gravitational field, but a rapidly spinning oblate neutron star is not a perfect sphere. Its equatorial bulge represents a slight asymmetry in its mass distribution. This asymmetry makes the star a continuous source of low-frequency gravitational waves. Unlike the violent, chirping waves from a merger, this would be a steady, humming note in the fabric of spacetime, a constant drone produced by its relentless spin and its distorted shape. While this signal is too faint for our current gravitational wave observatories to detect, its theoretical existence provides another avenue for future study. Detecting this continuous hum would allow us to measure the star's oblateness directly, giving us an unprecedented understanding of how this ultra-dense matter behaves under the stress of extreme rotation, effectively allowing us to weigh the strength of the nuclear force that holds it all together against the centrifugal force trying to tear it apart. This idea transforms the steady beat of pulsars from a scientific curiosity into a practical tool for interstellar exploration, creating a celestial navigation system that could guide humanity far beyond the familiar confines of our own solar system. The concept, often called pulsar-based navigation or a galactic positioning system, relies on the same fundamental principle as GPS on Earth, but on a vastly larger scale. Instead of relying on a constellation of human-made satellites in precise Earth orbits, this system would use nature's own timekeepers, millisecond pulsars, as its fixed reference points. These cosmic lighthouses are scattered throughout the galaxy, and their pulses arrive with a predictability that surpasses the best atomic clocks we can build. For a spacecraft venturing into the deep unknown, these distant, rhythmic signals become the fixed stars by which it can chart its course, offering a universal and autonomous method to find its way home from anywhere in the Milky Way. The mechanics of this system are both elegant and profoundly complex. A spacecraft will be equipped with a sensitive X-ray telescope specifically designed to detect the periodic signals from a pre-selected network of known millisecond pulsars. Each pulsar in this network has a unique signature, its specific position in the sky, and its incredibly stable pulse period. The spacecraft's onboard computer would contain a detailed ephemeris, a cosmic almanac listing the exact expected arrival time of pulses from each of these pulsars at a central reference point, such as the solar system's barycenter. As the spacecraft journeys through space, it would continuously monitor the actual arrival times of the pulses from several different pulsars. Because the spacecraft is at a different location in space than the solar system's center, the distance each pulse has to travel to reach the spacecraft will be slightly different. This creates tiny, measurable discrepancies between the expected arrival time and the actual arrival time. These are not errors, they are the key data points. By comparing the timing differences for multiple pulsars, essentially performing a form of celestial triangulation, the spacecraft's computer can solve for its unique position in three-dimensional space. It's analogous to how GPS works, but the baseline is not a few thousand miles between satellites, but the vast distances between stars. The precision is staggering. In theory, a spacecraft could determine its location to within a few hundred meters anywhere in the galaxy. This system would be entirely self-contained and would not require any communication with Earth, freeing future explorers from reliance on our increasingly distant home planet. As the vessel moves farther out, the signals from the pulsars remain just as reliable, their constancy providing a fixed grid against which all motion can be measured. It turns the entire galaxy into a mapped territory, with these spinning stellar corpses serving as the immutable signposts on an interstellar highway. The advantages of such a navigation system for long-duration, deep space missions are almost immeasurable. Consider a future mission to another star system. For years, the spacecraft will be traveling through the profound emptiness of interstellar space, with no nearby planets or landmarks to use for course correction. Radio signals from Earth would take years to arrive, making real-time guidance impossible. With a pulsar-based navigation system, the crew or the ship's autonomous systems could constantly and independently verify their position and velocity. If they began to drift off course, they would know immediately and could make tiny, precise adjustments to their trajectory, ensuring they don't miss their target by disastrously wide margins. This autonomy is crucial for the future of exploration, allowing probes and crewed vessels to operate intelligently without waiting for instructions that could take decades for a round-trip communication. Developing the technology to make this a reality is an active and thrilling area of research. NASA's Station Explorer for X-ray Timing and Navigation Technology, or Sextant, project has already demonstrated the core feasibility. Using the Neutron Star Interior Composition Explorer, or NICER, telescope mounted on the International Space Station, the Sextant team successfully used observations of millisecond pulsars to determine the space station's position in orbit around Earth. This was a critical proof of concept, showing that the incredible timing precision of pulsars can be translated into a real, working navigation solution. The next steps involve refining the sensitivity of the X-ray detectors, improving the algorithms that process the timing data, and creating a robust network of calibrated pulsars. We are, in effect, building the first prototypes of a technology that may one day guide our descendants on their journeys to other worlds, using the oldest and most reliable clocks in the universe as their guide. Just when scientists thought they were beginning to understand the rhythmic quirks of neutron stars, the cosmos presented them with a phenomenon that seemed to defy the very physics they had pieced together. It's called the anti-glitch, and it's an event so counterintuitive that it makes the familiar glitch look almost ordinary. While a standard glitch is a sudden, tiny speed up in the star's spin, an anti-glitch is the exact opposite, an abrupt, unexpected slowdown. Imagine listening to that hyper-precise cosmic metronome, and instead of it skipping ahead a beat, it suddenly hesitates and falls permanently behind. This isn't a gradual breaking from energy loss. It's a sudden, jarring deceleration, as if an invisible hand reached out and grabbed the star, slowing its furious rotation in an instant. The discovery of this behavior sent theorists back to their drawing boards, confronting them with a puzzle that required rethinking the complex dance between a neutron star's different layers. The most famous and thoroughly studied instance of this bizarre event occurred with the magnetar known as 1E2259+586. In April of 2012, a suite of space-based observatories, including NASA, Fermi, and Swift telescopes, witnessed this particular star do something extraordinary. It had a modest starquake and released a small flare of X-rays, which was not unusual for a magnetar, but hidden within the data was a far stranger signature. Alongside this activity, the star's rotation suddenly and measurably slowed down. It was a tiny change, a delay amounting to just a few millionths of a second per rotation. but for an object whose timing is tracked with nanosecond precision, it was a monumental shift. This was the anti-glitch, a clear and undeniable observation that the standard model of a sudden transfer of angular momentum from a faster spinning interior couldn't explain. If anything, that process should have made the star spin faster, not slower. So, what could possibly cause a city-sized object with the mass of a sun to suddenly put on the brakes? The leading theories are as fascinating as the event itself, and they all point to a dramatic upheaval within the star's hidden interior. One compelling explanation involves a sudden recoupling between the star's solid crust and its superfluid core. Recall that in a glitch, vortices in the superfluid unpin from the crust, transferring momentum outward and spinning it up. An anti-glitch might be the reverse, a sudden and massive repinning event. Imagine the superfluid core and the solid crust are rotating at slightly different speeds, with a complex boundary layer between them. If a vast number of superfluid vortices were to suddenly latch back onto the rigid structures of the inner crust, it would effectively create a powerful magnetic friction. The superfluid would violently grab onto the crust, transferring momentum inward and acting as a drag, causing the observable surface to suddenly slow down. It's as if the engine of a car suddenly seized up, its moving parts locking together and forcing the whole vehicle to lurch to a slower speed. Another, even more dramatic, theory suggests that the anti-glitch could be driven by a ferocious wind of particles being ejected from the star's surface. Magnetars possess the most powerful magnetic fields in the universe, and these fields can trap a vast, rotating atmosphere of charged particles just above the crust, known as the magnetosphere. During a period of intense magnetic stress, like a starquake, this entire magnetospheric structure could become unstable. If a colossal blob of this magnetized plasma was suddenly flung off into space, it would carry a tremendous amount of angular momentum with it. The conservation of angular momentum is a fundamental law. If a spinning object throws off mass, it must slow down to compensate. Think of an ice skater spinning with their arms outstretched. If they were to suddenly and violently throw a heavy weight away from their body, their spin would notably decrease. In the case of the magnetar, ejecting a portion of its own magnetosphere would act exactly like that thrown weight, applying a tangible brake to the star's rotation and producing the observed anti-glitch. The rarity of these events makes them incredibly valuable to scientists. While glitches are observed somewhat regularly in young, active pulsars, a confirmed anti-glitch remains a much rarer find. This scarcity itself is a clue, indicating that the conditions necessary to produce a sudden slowdown are far more special and extreme. They likely require the perfect storm of an incredibly strong magnetic field, a specific temperature profile in the interior, and a particular type of crustal fracture. The study of the anti-glitch in 1E2259 plus 586 provided the first hard data to test these exotic theories. By analyzing the precise timing of the slowdown in conjunction with the X-ray flare and starquake data, researchers could start to rule out some models and support others. Each of these events, therefore, is not a disruption to our understanding, but a refinement. They force our models of neutron star interiors to become more complex and more dynamic, accounting for the possibility that the relationship between the crust, the superfluid, and the magnetosphere can change in an instant, revealing a level of internal turbulence we are only just beginning to comprehend. And now we arrive at one of the most spectacular events in the cosmos, a collision of unimaginable violence and creative power, the merger of two neutron stars. Picture this: after spiraling inward for millions of years, drawn together by the relentless emission of gravitational waves, these two city-sized stellar corpses finally meet. In the last few seconds before impact, they are whirling around each other thousands of times per second, stretching and distorting each other with immense tidal forces. Their final embrace is not a gentle meeting, but a catastrophic collision, a cosmic car crash of unbelievable proportions. The energy released in that instant as they slam together is more than all the stars in the observable universe combined for a brief, glorious moment. It is from this unfathomable violence that new creation is born, forging the very elements that make up our world and our bodies in an event known as a kilonova. The detection of such an event on August 17, 2017, marked a watershed moment for astronomy, a triumph of multi-messenger observation. The event, named GW170817, began with a whisper in the fabric of spacetime. For about 100 seconds, the LIGO and Virgo gravitational wave observatories listened to the characteristic chirp of the two neutron stars as they spiraled ever closer, their orbits decaying until the signal culminated in a final, fierce crescendo as they merged. This was the first direct detection of gravitational waves from such a collision, but the story didn't end there. Just 1.7 seconds after the merger, NASA's Fermi Gamma Ray Space Telescope detected a short gamma-ray burst, a brilliant, fleeting flash of the highest energy light. This 1-2 punch of gravitational waves and gamma rays provided an unmistakable cosmic address, triggering a frantic global hunt. Within hours, telescopes all over the world and in space swiveled to that patch of sky, and the prize was found. A brand new, bright point of light in a galaxy called NGC 4993, located about 130 million light-years away. This was the kilonova, the visible and infrared afterglow of the merger's radioactive debris. So, what exactly is a kilonova, and why is its glow so significant? It is the brilliant radioactive signature of the rapid neutron capture process, or the R process, in action. When the two neutron stars merge, they don't just vanish. The collision shreds them, flinging a small but significant percentage of their ultra-dense, neutron-rich material out into space at velocities approaching the speed of light. This ejected material forms a hot, expanding cloud that is absolutely saturated with free neutrons. Within this cosmic crucible, atomic nuclei act as seeds, and they are bombarded by this incredible blizzard of neutrons. Because the density is so high, neutrons are captured by the seed nuclei much faster than the resulting unstable isotopes can radioactively decay. It's like a snowball rolling down a hill, gathering more snow so quickly it never has a chance to melt. A single nucleus can swell in size, climbing up the periodic table in a matter of seconds to form extremely heavy, unstable elements. This frantic climb is followed by a period of consolidation. These overstuffed, neutron-rich nuclei are inherently unstable and begin to decay back toward stability, transforming neutrons into protons through a series of radioactive decays. It is this decay process that powers the kilonova's glow and forges entirely new, stable elements. The initial expansion produces a hot, blue glow, but as the cloud expands and cools, and as heavier elements with more complex atomic spectra form, the light shifts to the red part of the spectrum over the course of a few days. This change in color is a key observational signature of a kilonova. The specific elements produced in this cosmic alchemy include a significant portion of the universe's heaviest elements, including gold, platinum, uranium, and other rare earth elements. Scientists estimate that the single merger event GW170817 produced an amount of gold equivalent to hundreds of times the mass of the entire Earth, along with vast quantities of other precious elements, scattering them across the galaxy to one day be incorporated into new generations of stars and planets. This direct link between neutron star mergers and the creation of heavy elements fundamentally rewrites our understanding of our own cosmic origins. Every single piece of gold in a wedding ring, every trace of platinum in a catalytic converter, and even the radioactive uranium that provides power, all originated in the violent aftermath of a cataclysm like GW170817. The material was forged billions of years ago in a galaxy far away, long before our own solar system formed. That enriched material was then scattered across space, eventually mixing with the giant molecular cloud that would collapse to form our Sun and its planetary system. This means that the atoms of these heavy elements within our bodies and our world are literal stardust, but not from the gentle furnaces of normal stars. They are the ashes of a catastrophic collision between two of the universe's most extreme objects. We are, in a very tangible sense, the children of these incredible cosmic explosions. But as we push our understanding of matter to its absolute limits, we must confront one of the most radical and speculative ideas in all of astrophysics, the possibility that what we call a neutron star might not be made of neutrons at all. This is the strange star hypothesis, a theory that proposes the most ultra-dense objects in the universe could be composed of something even more exotic and fundamental, a soup of pure quarks. In this mind-bending scenario, the immense gravitational pressure doesn't just stop at crushing atoms into a sea of neutrons. It goes a step further, overwhelming the strong nuclear force itself and crushing the neutrons until they literally pop open, spilling their constituent parts into a new state of matter known as strange matter. A strange star wouldn't have a solid crust or a neutron ocean. It would be a single, gigantic atomic nucleus the size of a city, but one made of quarks that have broken free from their confinement. The driving force behind this idea is a concept known as the Bodmer-Witten hypothesis, which suggests that this strange matter, a mixture of up, down, and strange quarks, could be the most stable form of matter in the entire universe, more stable than even the iron that sits at the heart of stars. In our everyday world, quarks are forever locked in groups of 2 or 3, bound by the strong force to form protons and neutrons. But under the astronomical pressures inside a neutron star, the energy cost of confining quarks might become too high. It could be energetically favorable for them to break free and form a vast, uniform soup where they can all move around more freely. The strange quark gets its name because it's heavier and more exotic than the common up and down quarks that make up normal matter, and its inclusion in the mix is thought to lower the overall energy of the system, creating this potentially ideal stable state. If this hypothesis is correct, then the entire neutron star would be a single, enormous droplet of this quark gluon plasma, from its surface all the way to its core, with no distinct layers at all. How could we possibly tell the difference between a city-sized droplet of strange matter and a conventional neutron star from billions of light years away? The key lies in the subtle but critical differences in their physical properties, primarily their size and how they respond to extreme forces. A strange star would be inherently more compact. Because quark matter can be compressed more easily than matter made of whole neutrons, a strange star of the same mass as a neutron star would have a significantly smaller radius. Imagine two balls of the exact same weight, but one is made of stiff, rigid material and the other is made of a more pliable, dense substance. The pliable one will be smaller. This size difference is a potential observational signature. By using techniques like analyzing the X-ray, bursts from binary systems, or the gravitational waves from mergers, astronomers can attempt to measure the relationship between a compact object's mass and its radius. If they find one that is unexpectedly tiny for its mass, it could be a strong candidate for a strange star. Another telling signature could be how these objects spin without flying apart. The maximum possible spin rate for a compact object is set by its breakup limit, the point where centrifugal force overcomes gravity. A strange star, being more compact and bound by different forces, would have a different maximum spin than a neutron star. Some theorists have even proposed that tiny, asteroid-sized chunks of strange matter could exist called strangelets. If a strangelet were to ever collide with a normal matter object, a fantastical and terrifying process called strange matter conversion could occur, where it would transform the normal matter it touches into more strange matter, releasing a tremendous amount of energy. While this is purely speculative and there's no evidence it happens, the theoretical possibility highlights the profoundly different nature of this hypothesized substance. The hunt for these strange stars is ultimately a hunt for the true ground state of matter, pushing our understanding of the fundamental laws of physics into realms we can only otherwise glimpse for fractions of a second in the world's most powerful particle colliders. Now consider the constant, invisible rain of high-energy particles that relentlessly pelts our planet from the depths of space. These are cosmic rays, not rays of light, but atomic nuclei, mostly protons, traveling at nearly the speed of light, carrying energies that dwarf anything we can produce in our most powerful particle accelerators like the Large Hadron Collider. For over a century, the origin of the most energetic of these particles has been one of astronomy's most enduring mysteries. Where in the universe are the natural cannons capable of firing subatomic bullets with such staggering force? The evidence is increasingly pointing to the frenetic environments surrounding neutron stars, where the combination of insane magnetic fields and violent shocks creates the perfect engine for particle acceleration on a truly cosmic scale. The most compelling evidence for this comes from the beautiful and complex structures known as pulsar wind nebulae. Imagine a pulsar, a rapidly spinning neutron star, acting like a colossal natural generator. Its rotation and magnetic field combine to blow out a relentless magnetized wind of electrons and positrons, flowing away from the star at almost light speed. This isn't a gentle breeze, it's a hurricane of charged particles. As this pulsar wind races outward, it eventually smashes into the slower-moving material of the surrounding interstellar medium, or even into the debris from the star's own supernova explosion. This collision creates a massive, standing shock wave, a cosmic traffic jam where particles pile up and are processed with unimaginable violence. It is at this turbulent boundary, this natural particle accelerator light years across, where the real magic happens. The process that energizes particles here is a theorized mechanism called Fermi acceleration or diffusive shock acceleration. Picture a subatomic particle like a proton caught in the chaotic magnetic fields on either side of the shock front. The particle bounces back and forth as if trapped between two converging magnetic mirrors. Each time it crosses the shock front, it gains a little bit of energy from the motion of the shock itself. It's like a tennis ball being volleyed back and forth between two approaching rackets. With each impact, the ball flies faster and faster. In a pulsar wind nebula, a particle can make countless cycles across this boundary, and with each pass, its energy increases. Since the shock is stationary and the magnetic fields are immense, particles can be trapped in this process for long periods, eventually being flung out into the galaxy with energies millions of times greater than those achieved in any human-built machine. The Crab Nebula provides the most famous and well-studied example of this incredible engine in action. At its heart spins the Crab Pulsar, a neutron star born in the supernova observed by Chinese astronomers in 1054. The pulsar's fierce wind has inflated a magnificent nebula that glows across the electromagnetic spectrum. Most importantly, we observe that the Crab Nebula is a brilliant source of high-energy gamma rays, the telltale signature of particles being accelerated to extreme velocities. The gamma rays are produced when these ultra-energetic particles interact with magnetic fields or light, and their intensity tells us that the nebula is operating as a continuous, powerful particle accelerator. This direct observation provides a compelling case study for how isolated neutron stars can be responsible for generating a significant portion of the cosmic rays that permeate our galaxy. But the true power of these cosmic accelerators may be revealed in even more extreme systems. When neutron stars exist in binary pairs with massive companion stars, the situation becomes even more potent. The intense radiation and particle wind from the pulsar can strike the stellar wind blowing off the companion, creating a colossal shock wave right at the boundary between the two stars. This setup creates a confined and exceptionally efficient acceleration site. Furthermore, the supernova explosions that create neutron stars are themselves titanic shocks that can blast particles to high energies. While the remnants of these explosions may fade over thousands of years, the pulsar wind nebulae within them can continue to operate for much longer, providing a long-lasting source of power. This combination of sources suggests that neutron stars, in their various forms, could be responsible for a substantial fraction of the galactic cosmic rays we detect, those mysterious messengers from a universe filled with invisible, high-energy fury. From its cataclysmic birth to its ultimate cold and dark demise, the life cycle of a neutron star is an epic saga spanning timescales that dwarf human history. This incredible journey begins, as we've explored, in the furious inferno of a core collapse supernova, when a massive star, at least 8 times heavier than our Sun, exhausts its nuclear fuel. Its iron core can no longer resist the crushing force of gravity. In less than a second, it implodes, collapsing from a sphere the size of Earth down to a city-sized ball of neutrons. The rebounding shockwave blasts the star's outer layers into space, creating a brilliant supernova that can outshine entire galaxies, while the newborn neutron star is left behind as a searingly hot, rapidly rotating cinder. Many receive a powerful kick from an asymmetrical explosion, shooting them across the galaxy like cosmic cannonballs, destined for a lonely existence, while others remain gravitationally bound to a companion star, setting the stage for a very different kind of future. For the first several thousand years of its life, a young, isolated neutron star is a tempestuous and energetic object. Its surface, glowing at over 1,000,000 degrees Celsius, emits intense X-rays, and if its magnetic poles are misaligned with its rotation axis, it announces itself to the universe as a pulsar, a rhythmic lighthouse beacon. During this vigorous youth, the star cools with incredible efficiency, not by radiating light from its surface, but by producing a flood of neutrinos from its ultra-dense core. These ghostly particles stream out unimpeded, carrying away the star's birth heat and causing its temperature to plummet. Its rapid spin also begins to slow down as it radiates energy away through its powerful magnetic fields and relativistic particle winds. This is the most active and observable phase, where we witness starquakes, glitches, and, in the case of magnetars, colossal flares that reshape the star's very structure. The middle age of a neutron star, spanning from about 100,000 to several million years, is marked by a transition to a more stable but gradually fading existence. By this point, the furious neutrino cooling has subsided, and the star now loses heat primarily through thermal radiation from its surface, glowing steadily in X-rays. Its rotation has slowed significantly, and the regular pulses of a pulsar become weaker and harder to detect. The magnetic field, a source of so much youthful volatility, has also decayed substantially, often by a factor of 1,000 or more. A magnetar, for instance, will have calmed down, its apocalyptic magnetic field having relaxed to a level where it can no longer power giant flares, transitioning into a more ordinary, rotation-powered pulsar. This is a long period of quiet slowing and cooling, a cosmic adulthood where the star steadily ticks down, its once ferocious energy ebbing away into the void. However, for a neutron star lucky enough to have a stellar companion, this middle age can be anything but quiet. If it's in a close binary system, it can embark on a dramatic second act known as recycling. The neutron star's immense gravity acts as a cosmic vampire, relentlessly pulling gas from its companion. This material doesn't fall directly onto the surface, it spirals in, forming a superheated accretion disk. As this stolen matter crashes onto the neutron star's surface, it does two things. It releases a torrent of X-rays, making the system brilliantly visible, and it transfers angular momentum, spinning the neutron star back up. Over millions of years, this process can accelerate the pulsar to mind-numbing speeds, transforming an old, slow-spinning relic into a millisecond pulsar, rotating hundreds of times per second. This is a profound rebirth, giving the stellar corpse a new lease on life and a new role as one of the most precise clocks in the universe. But this cosmic vampirism cannot continue forever. The binary system's fate depends on the mass and evolution of the companion star. In some cases, the neutron star may completely evaporate its partner, creating a black widow system and leaving itself isolated once more, albeit now as a rapidly spinning millisecond pulsar. In other, more catastrophic scenarios, the companion star itself may go supernova. If the explosion is not perfectly symmetrical, it can kick the binary system apart, sending both stellar remnants flying off on separate paths through the galaxy. Alternatively, if the binary survives this second explosion, the result can be an even more exotic system: two neutron stars orbiting each other, destined to spiral inward over billions of years until they finally merge in a spectacular kilonova that forges gold and platinum and ripples the fabric of spacetime. Ultimately, regardless of its path, every neutron star faces the same final fate in the far, far future. After billions of years, it will have cooled to a temperature barely above absolute zero, becoming a cold, solid crystal of ultra-dense matter. Its rotation will have slowed to a near standstill, and its magnetic field will have faded to insignificance. It will become a dark, inert stellar fossil, a black dwarf drifting silently through the galaxy. This is the expected end for the vast majority of neutron stars. A quiet, cold, and eternal fade to black over timescales so long that the universe has not yet existed long enough for a single neutron star to reach this state. There is, however, one final, violent alternative. If a neutron star in a binary system continues to accrete matter and its mass pushes past the Tolman-Oppenheimer-Volkoff limit, somewhere between 2.1 and 2.3 solar masses, the final battle between quantum pressure and gravity is lost. Neutron degeneracy pressure, the very force that halted its initial collapse, catastrophically fails. In an instant, there is nothing left in the universe that can support it. The entire structure implodes, vanishing from sight as it collapses into an infinitely dense singularity, leaving behind only an event horizon, a black hole. This dramatic end transforms one of the universe's most extreme objects into the only thing more extreme, a final, silent testament to the ultimate, irresistible power of gravity. While we've been charting the incredible physics of these distant stellar cinders, the monumental challenge lies simply in seeing them at all. Pushing our vision to the very edge of the observable universe to spot an object only 12 miles wide is arguably one of the greatest technical endeavors in all of modern science. The primary obstacle is a brutal combination of their minuscule apparent size and their mind-boggling remoteness. Even the most brilliant neutron star, pouring out immense energy, becomes an impossibly faint speck after its light has traveled for billions of years through the expanding cosmos. Detecting this feeble signal is like trying to spot a single firefly hovering next to a lighthouse from 10,000 miles away, while that lighthouse itself is dimmed by a thick cosmic fog. This isn't just a matter of building a bigger telescope. It's a battle against the fundamental limits of physics and the sheer, empty volume of the universe itself. Our current fleet of telescopes, as advanced as they are, operates right at this bleeding edge. In the X-ray spectrum, where the hot surfaces and violent accretion disks of neutron stars shine brightest, the Chandra Observatory has been a revolutionary workhorse. Yet, for every distant neutron star we detect, there are undoubtedly thousands more whose X-ray photons are simply too sparse to register above the background noise of the cosmos by the time they reach Chandra's instruments. In the radio band, where we listen for the rhythmic pulses of pulsars, the signal faces a different kind of decay. The vast arrays of radio dishes act as colossal ears, but the faint, regular beat of a distant pulsar can be completely scattered and smeared out by the charged particles of the interstellar medium it traverses. It's akin to trying to hear a whispered melody from across a roaring stadium. The message is there, but it's drowned and distorted by the environment long before it reaches the listener. Compounding this problem of sheer distance is the pervasive interference from cosmic dust and gas. The space between stars is not a perfect vacuum. It's filled with tenuous clouds of hydrogen molecules and microscopic silicate or carbon dust grains. This interstellar medium acts like a gentle but persistent veil. For optical light, this dust is utterly opaque, blocking the view entirely. This is why we cannot see the center of our own galaxy in visible light. For higher energy radiation like X-rays, the effect is different but still significant. While X-rays can punch through dust clouds more easily, they are not immune. They can be absorbed or scattered by atoms in their path, and over intergalactic distances, these tiny interactions add up, further dimming the already feeble signals we so desperately seek. Every photon that finally makes it to our detectors is a cosmic champion, having survived an epic journey through a minefield of obscuration. The future of this field, however, is dazzlingly bright, thanks to a new generation of observatories designed to overcome these very limitations. The James Webb Space Telescope, while famed for its infrared gaze into the early universe, plays a crucial supporting role. Its powerful instruments can precisely measure the redshifts and properties of the host galaxies that contain these distant neutron stars, providing the essential cosmic context that X-ray and radio telescopes cannot. By combining Webb's detailed galactic portraits with Chandra's high-energy detections, we can confirm the phenomenal distances of these objects and study the stellar environments that birthed them. But the true game-changer on the horizon is the Square Kilometre Array, or SCAR. This is not a single telescope, but a revolutionary project to build the world's largest radio observatory, with thousands of dishes spread across South Africa and Australia, creating a collective receiving area of, as the name implies, a square kilometre. The SCA's sensitivity will be so profound that it will be able to detect the faint radio pulses from pulsars at distances far beyond our current capabilities, effectively taking a census of neutron stars across a vast volume of the universe. Furthermore, its incredible resolution will allow it to peer through interstellar scattering with unprecedented clarity, cleaning up the smeared signals and revealing the pristine pulse profiles of pulsars we can currently only dream of detecting. It will be like upgrading from a staticky AM radio to a high-fidelity digital receiver for the entire cosmos. These upcoming instruments represent more than just incremental improvements. They are a fundamental shift in our ability to explore. They will allow us to move from studying a handful of rare, extremely bright distance record holders to analyzing a large population of neutron stars at various cosmic epochs. This statistical power is key. By comparing the properties of neutron stars born in the early universe with those formed more recently, we can track how their formation and evolution have changed over cosmic time. We can test if the first neutron stars were somehow different, more massive, more magnetic than their modern counterparts. These next-generation observatories will transform these distant specks from astronomical curiosities into a rich data set, finally allowing us to write a comprehensive history of these cosmic powerhouses from their origins at the dawn of time to the present day. Perhaps the most profound realization in our study of these objects is that no two neutron stars are exactly alike. Just as people are shaped by their experiences and environments, the life of a neutron star is a story written by its initial spin, the strength of its magnetic field, and the company it keeps. This has led to the discovery of distinct populations, each with its own unique personality and behavior in the cosmic landscape. The most common and iconic type is the rotation-powered pulsar. Think of these as the universe's frugal energy users. Their brilliant lighthouse beams and powerful particle winds are fueled solely by their reservoir of rotational energy, the spin they were born with. As they blast radiation into space, they gradually slow down, their rotation acting like a cosmic battery that is slowly, over millions of years, being drained. These are the steady, predictable metronomes we often use for navigation and testing fundamental physics. Their characteristic is a slow, relentless increase in their pulse period as they lose energy, ticking away the eons until they eventually spin down too much to be easily detected. Then there are the accretion-powered pulsars, the cosmic vampires we've encountered in binary systems. These neutron stars have a completely different energy source, gravity. By pulling matter from a companion star, they tap into the immense gravitational potential energy released as that gas spirals down onto their surface. This process makes them shine brilliantly in X-rays, and it can have a dramatic effect on their spin. Unlike their rotation-powered cousins, which are always slowing down, accretion-powered pulsars can actually be spun up. The infalling material carries angular momentum, acting like a cosmic hand that gives the neutron star a continuous push, potentially accelerating it to become a millisecond pulsar. The presence of a steady, bright X-ray glow and the potential for the spin period to either increase or decrease depending on the balance of accretion torques are the hallmarks of this population. They demonstrate that a neutron star's destiny can be completely rewritten by a nearby partner. Occupying the most extreme end of the magnetic spectrum are the magnetars. If a typical neutron star's magnetic field is impressive, a magnetars is apocalyptic, measuring 1,000 trillion times stronger than Earth's. These are not steady lighthouses, they are volatile, twitching titans. Their primary energy source is the immense power stored in their twisted, evolving magnetic fields. This makes them prone to violent outbursts, starquakes, and giant flares that can momentarily outshine entire galaxies in high-energy radiation. A magnetar's life is one of dramatic upheaval. In their youth, they are racked by frequent eruptions as their internal magnetic fields readjust and their crust fractures under the strain. Over time, as their colossal magnetic fields decay and their internal structure settles, they often transition into more ordinary, rotation-powered pulsars. Their story is one of tempestuous youth giving way to a quieter, more stable adulthood. A more enigmatic and recently identified population is known as Central Compact Objects, or CCO. These are lonely neutron stars found sitting quietly at the centers of supernova remnants, but with a puzzling set of characteristics. They are typically very faint in radio waves, so we don't detect the classic pulses of a pulsar. They also have surprisingly low magnetic fields, about 100 times weaker than those of an ordinary pulsar. This presents a fascinating mystery. How can a neutron star be born with such a weak magnet? The leading theory is that these objects are actually hiding their true strength. It's possible that soon after their birth, a rapid fallback of supernova material buried their incredibly strong magnetic field beneath a newly formed solid crust. Over thousands of years, this buried field is only now slowly diffusing back to the surface. CCOs may therefore be young magnetars in disguise, their terrifying power still mostly locked away, waiting to be revealed as they age. This incredible diversity is not random. It is a direct consequence of a neutron star's history. Its age determines how much it has cooled and spun down. The initial strength of its magnetic field sets its potential for violent activity. Its environment, whether it is isolated, has a binary companion, or sits within a supernova remnant, dictates its primary source of energy and how it evolves. And its history of mass accretion can completely reset its rotational clock, turning an old, slow star into a rapid-fire millisecond pulsar. By classifying these objects and understanding the forces that shape them, we are doing more than just creating a celestial catalog. We are learning to read their life stories, tracing the pathways of stellar evolution from a violent, incandescent birth to a final, cold, dark destiny. Each population is a different chapter in the same epic tale, revealing how the universe nurtures and transforms matter under the most extreme conditions imaginable. And that brings us to a pivotal shift in how we perceive the cosmos, a true revolution in our observational capabilities where neutron stars have taken center stage. We are now living in the era of multi-messenger astronomy, a time when we no longer just look at the universe, but we listen to it, feel its vibrations, and even detect its ghostly particles, all to piece together a complete story. For centuries, our entire understanding of the heavens was built upon light from the visible rays that hit our retinas to the radio waves, X-rays, and gamma rays captured by our telescopes. But light can be blocked, scattered, or absorbed by cosmic dust, and it only tells one part of a much richer tale. Multi-messenger astronomy shatters this limitation by adding new, fundamental senses to our cosmic perception. We now detect the ripples in spacetime itself, known as gravitational waves, and we catch elusive particles called neutrinos that fly straight through matter as if it weren't even there. When we combine these different messengers with traditional light, it's like moving from a silent black and white film to a full-color, high-definition, surround sound experience of a cosmic event. And neutron stars, with their incredible densities and violent interactions, are the perfect actors in this new multi-sensory theater, producing signals across this entire spectrum and allowing us to witness their most dramatic moments with a clarity we once thought impossible. The historic binary neutron-star merger detected in August 2017, known as GW170817, stands as the iconic proof of concept for this powerful approach. The event began with a whisper in the fabric of reality, a gravitational wave signal picked up by the LIGO and Virgo observatories. For 100 seconds, their instruments recorded the characteristic chirp of two neutron stars spiraling inward, a direct testament to Einstein's theory playing out on a cosmic stage. This signal alone told us the masses of the objects and the rough area of the sky they were in. But the story exploded into life just 1.7 seconds later, when NASA's Fermi satellite detected a short, powerful burst of gamma rays from the same patch of sky. This 1-2 punch of gravitational waves and light was the trigger that set off a global frenzy. Astronomers across the world pointed every available telescope, optical, infrared, ultraviolet, and X-ray toward the source. What they found was a new, bright spot in the galaxy NGC 4993, the kilonova, the brilliant, radioactive glow of heavy elements being forged in the merger's debris. This single event connected the physics of gravity, the creation of the elements, and the dynamics of a stellar explosion into one coherent, breathtaking narrative. It was multi-messenger astronomy in its fullest glory, and it confirmed that we are no longer passive viewers of the cosmos, but active participants in decoding its grandest spectacles. Each cosmic messenger provides a unique and irreplaceable piece of the puzzle, like different specialists called to a crime scene. Light, across all its wavelengths, tells us about the thermal and chemical properties of an event. The specific colors and how they change over time revealed the kilonova's composition, showing us the signature of gold, platinum, and other heavy elements being created in real time. Gravitational waves, on the other hand, are the direct reporters of dynamics and mass. They are untouched by gas or dust and carry pure information about the motion of massive objects. From the gravitational wave signal of a merger, we can deduce the masses and spins of the neutron stars, the precise dynamics of their final orbits, and even probe the stiffness of their internal matter. Then there are neutrinos, the ghostly particles that are so notoriously difficult to detect. In a core collapse supernova, the birth cry of a neutron star, 99% of the colossal energy is carried away not by light or gravitational waves, but by a tremendous flood of these neutrinos. Detecting that neutrino pulse is like having a probe inside the collapsing stellar core at the very moment of creation, offering a direct look at the physics of the proto-neutron star that light could never penetrate. By combining all these signals, we cross-check our models, confirm our theories, and discover new physics that would remain completely hidden if we relied on any single messenger alone. The future of this field is being built right now, with a new generation of observatories designed to work in concert, turning rare, singular events into a routine stream of rich data. The gravitational wave detectors like LIGO, Virgo, and Japan's Kagra are undergoing constant upgrades to increase their sensitivity, which will allow them to hear neutron star mergers from farther away and with greater precision, pinpointing their locations in the sky with astonishing accuracy. In space, the planned Laser Interferometer Space Antenna, or LISA, will open up a new low-frequency gravitational wave band, potentially allowing us to hear the continuous hum from millions of binary systems, including those with neutron stars, and even detect the mergers of supermassive objects. For neutrinos, gigantic detectors like IceCube at the South Pole and the upcoming KM3 NET in the Mediterranean Sea are expanding our ability to catch these elusive particles and trace them back to their astrophysical sources. And orbiting observatories like the James Webb Space Telescope and its successors will be ready to swiftly turn their powerful gaze toward the sources of these signals, analyzing the aftermath of cosmic explosions with unprecedented detail. This global, interconnected network of instruments is transforming astronomy from a solitary pursuit into a collaborative, real-time enterprise, where an alert from a gravitational wave detector in Louisiana can trigger a coordinated observation by telescopes on every continent and in space, all working together to capture the full, multi-messenger story of a single neutron star's most dramatic moment. Now, we come to a genuine detective story in the field of high-energy astrophysics, a case of a missing stellar corpse that has left scientists scratching their heads for decades. When a massive star goes supernova, the textbooks tell us a neutron star should be left behind, a dense cinder sitting right at the heart of the expanding cloud of debris we call a supernova remnant. Yet, when astronomers point their most powerful telescopes at the centers of many young, well-studied remnants, they often find nothing. No pulsing beacon, no steady X-ray glow, just an eerie and inexplicable emptiness. This is the missing neutron star problem, and it's a paradox that forces us to reconsider the final moments of a star's life and the bizarre fates that can befall its remains. It's as if a detective arrived at the scene of a massive explosion, confirmed a death occurred, but found no body in the wreckage, prompting a series of compelling and sometimes dramatic theories about what could have happened. One of the most plausible solutions is that the neutron star isn't actually missing at all, it's just playing an incredible game of cosmic hide and seek. The culprit could be its own unimaginably strong magnetic field. In the chaotic moments after a supernova, an immense amount of stellar material can fall back onto the newborn neutron star. This deluge of matter might effectively bury its incredibly powerful magnetic field beneath a newly formed, heavier layer of crust. What remains is a neutron star with a surprisingly weak surface field, one that doesn't generate the energetic processes needed to power a bright pulsar wind or X-ray emission. These hidden objects are known as central compact objects, or CCO. They are detected only by a faint, steady glow of thermal X-rays from their hot surfaces, with no radio pulses and no pulsar wind nebula to announce their presence. They are the cosmic equivalent of an engine that's been flooded. All the components are there, but the spark needed to turn it on has been temporarily smothered. Over thousands of years, the buried magnetic field is thought to slowly diffuse back to the surface, and the CCO may eventually turn on and reveal itself as a more typical pulsar. But for now, it remains a quiet, dark specter at the center of its own remnant. A far more violent explanation is that the neutron star received such a tremendous kick at its birth that it was literally shot out of its own home. Supernova explosions are rarely perfectly symmetrical. If more material and energy are blasted out in one direction, the newborn neutron star will recoil in the opposite direction, just like a rocket. These natal kicks can be astoundingly powerful, propelling the star at hundreds of kilometers per second. In the most extreme cases, a neutron star can achieve hypervelocity, moving so fast that it quickly overtakes the expanding shell of its supernova remnant and escapes into interstellar space entirely. Imagine a bullet fired from a gun that then races ahead of the smoke cloud from the barrel. From our distant perspective, we would see the smoke cloud, the beautiful supernova remnant, but the bullet itself would be long gone, a lonely traveler speeding through the darkness. This means that when we admire the intricate, glowing filaments of a supernova remnant like IC443, the neutron star that created it might already be light years away, completely disconnected from the beautiful chaos it left behind. There exists a third, even more extreme possibility. What if the missing neutron star collapsed directly into a black hole? This could happen if the original star was so immensely massive that the collapsing core itself exceeded the Tolman-Oppenheimer-Volkoff limit, the maximum mass a neutron star can support. In this scenario, the core's collapse would never be halted by neutron degeneracy pressure. Instead of forming a neutron star, it would continue to implode relentlessly, vanishing from the observable universe behind an event horizon. There would be no stellar corpse to find because the corpse was never stable to begin with. It immediately became something else, something that emits no light of its own. Alternatively, a neutron star could be born normally but then quickly consume itself. If it is in a binary system and begins to voraciously accrete matter from its companion, the added mass could push it over the critical limit. Like a sponge that can only hold so much water before it disintegrates, the neutron star would succumb to its own weight, collapsing into a black hole and effectively erasing itself from view shortly after its birth. Each of these theories, the hidden CCO, the runaway star, or the prompt collapse, paints a different picture of stellar death, showing that the aftermath of a supernova is not a single predictable outcome, but a range of dramatic possibilities that depend on the mass, spin, and environment of the progenitor star. To truly understand the invisible forces and hidden structures of a neutron star, scientists must go beyond observation and step into the role of cosmic architects, building these incredible objects from scratch inside the world's most powerful supercomputers. This isn't about creating a simple animation. It's about solving the universe's most complex equations in 3 dimensions, simulating the very laws of physics to watch a neutron star be born, live, and die in a breathtakingly detailed digital universe. The challenge is staggering. A single simulation must account for the mind-bending rules of Einstein's general relativity, the turbulent chaos of magnetohydrodynamics, the subtle interactions of subatomic particles through the weak nuclear force, and the quantum behavior of matter at densities 1 trillion times greater than steel. No single human brain could ever hold all these variables at once, which is why researchers turn to colossal supercomputers, machines that can perform quadrillions of calculations per second to act as their digital laboratories for the impossible. The process begins with a set of fundamental equations and a grid that represents a portion of space. For a core collapse supernova simulation, scientists start with a model of a massive, dying star in the final moments of its life. They program in the initial conditions the star's mass, composition, rotation, and magnetic field strength. Then they set the rules, the laws of gravity, nuclear physics, and fluid dynamics. When they press Run, the supercomputer begins a frantic calculation. It divides the star into hundreds of millions or even billions of tiny cells. For each cell, at each infinitesimal step in time, it calculates the local temperature, density, pressure, and the flow of energy and neutrinos, watching as the iron core becomes unstable, begins to collapse, and then rebounds in a titanic shockwave. These simulations are so computationally expensive that they can run for months on thousands of processors simultaneously, consuming millions of CPU hours to recreate just a few seconds of real-world time. The goal is to see if their digital star will successfully explode and what kind of neutron star or black hole it leaves behind, providing crucial insights into one of the universe's most violent and pivotal events. Once a neutron star is born, simulations shift to exploring its long-term evolution and bizarre internal dynamics. A key target is understanding pulsar glitches and the strange superfluid behavior of the neutron star's interior. Researchers create a model that separates the star into different components: the solid, crystalline crust, the superfluid neutron ocean beneath it, and the potentially exotic quark matter core. They then apply the physics of quantum vortices, trillions of microscopic whirlpools in the superfluid that can become pinned to the crust structure. By simulating the gradual slowdown of the crust and the resulting stress on these pinned vortices, scientists can watch as the system reaches a breaking point. In the simulation, they witness a starquake or a massive vortex unpinning event occur, seeing a sudden transfer of angular momentum that spins up the crust, perfectly mirroring the real-world glitches observed by radio telescopes. This allows them to test different models of the interior, determining the breaking strain of the crust and the viscosity of the superfluid by seeing which simulated parameters produce glitches that match the size and frequency of those we actually detect in the cosmos. Perhaps the most visually spectacular and scientifically fruitful simulations are those of binary neutron star mergers. Here, the computational challenge is even greater, as it requires tracking two ultra-dense objects in a delicate gravitational dance, each warping spacetime around them as they spiral inward over thousands of orbits. These simulations are crucial for interpreting the gravitational wave signals detected by LIGO and Virgo. The simulated merger unfolds in several dramatic phases. First, the two stars, distorted into teardrop shapes by tidal forces, spiral closer and closer. As they make contact, the simulation shows their surfaces tearing apart, flinging a spray of hot, neutron-rich material into space, the raw fuel for the kilonova and the R-process creation of heavy elements. The cores of the two stars then collide, either merging into a hypermassive neutron star that spins furiously, supported by its differential rotation, or promptly collapsing into a black hole, depending on the total mass and the stiffness of the equation of state programmed into the simulation. The output of these merger simulations is a treasure trove of synthetic data. From the simulation, scientists can extract the precise gravitational waveform that such an event would produce. They can then compare this simulated waveform to the real one detected by observatories. If the real signal shows certain features like a prolonged oscillation after the merger, it suggests the formation of a massive neutron star remnant rather than an immediate collapse to a black hole. Furthermore, the simulation tracks the amount, composition, and velocity of the ejected material. By feeding this data into a separate simulation of the kilonova's radioactive glow, they can predict what the electromagnetic aftermath should look like, allowing astronomers to know exactly what to search for with their telescopes. This powerful synergy between simulation and observation turns a detected signal into a rich story, revealing not just that a merger happened, but exactly how it happened, what it created, and what it tells us about the fundamental nature of ultra-dense matter. Ultimately, these digital experiments are our primary tool for exploring the equation of state of neutron star matter, the holy grail of high-density physics. Since we cannot recreate these conditions on Earth, supercomputers provide the only testing ground. Scientists run entire families of simulations, each one using a slightly different assumption about how matter behaves at these extreme densities. One set might assume a very soft equation of state where the core is compressible and contains exotic particles. Another set might use a stiff equation of state where matter strongly resists compression. They then compare the results of all these different simulations against real-world observations, the measured masses and radii of neutron stars, the gravitational waves from mergers, and the properties of pulsar glitches. The simulations that produce results consistently in conflict with reality are ruled out. Those that successfully reproduce the universe we see are kept and refined. In this way, supercomputers act as a cosmic filter, sifting through countless theoretical possibilities to guide us, step by simulated step, toward the one true physical law that governs the heart of an atom pushed to its absolute limit. Beyond their profound scientific significance, these cosmic powerhouses have also carved out a remarkable niche within our collective imagination, fueling countless stories and inspiring awe on the silver screen and in the pages of science fiction. They serve as the ultimate exotic backdrop, representing the final frontier's most unforgiving and mysterious realms. In many narratives, a neutron star is less a scientific object and more a formidable character in its own right, a cosmic siren whose immense gravitational pull and lethal radiation present an almost insurmountable obstacle for intrepid spacefarers. This portrayal taps into a very human fear and fascination with the unknown, transforming complex astrophysics into a visceral, dramatic confrontation between technology and the raw, untamed power of the universe. The sheer otherworldliness of an object where a teaspoon of material weighs billions of tons provides a fertile ground for storytellers to explore themes of survival, hubris, and the limits of human ingenuity when faced with forces beyond comprehension. One of the most common and thrilling tropes is the neutron star as a navigational hazard or a terrifying trap. The concept of spaghettification, where the tidal forces stretch any object into a stream of atoms, becomes a grisly fate for unlucky spacecraft that wander too close. This idea was spectacularly visualized in the film Event Horizon, where the titular ship's experimental gravity drive tears a hole into a hellish dimension, a concept heavily inspired by the theoretical warping of spacetime around ultra-dense objects. While not a literal neutron star, the visual and narrative language is directly borrowed from the physics of these remnants. The star's gravity well becomes a predatory feature, an inescapable whirlpool in the void that requires pinpoint precision and courage to navigate. This transforms the cold equations of orbital mechanics into a white-knuckle race against time, making the audience feel the desperate tension as fictional crews calculate slingshot maneuvers around these spinning demons, riding the edge of their gravitational influence to gain a speed boost or make an impossible escape. Beyond mere obstacles, neutron stars are often reimagined as immense power sources or even engineered artifacts, pushing the boundaries of speculative technology. The concept of a Dyson sphere, a hypothetical megastructure built around a star to harness its entire energy output, has been adapted around these denser objects. A civilization advanced enough to encapsulate a neutron star could theoretically tap into the phenomenal energy of its rotation and magnetic field, creating a power source for interstellar travel or even computation on an unimaginable scale. This theme was explored to a breathtaking degree in Liu Cixin's renowned novel The Three-Body Problem and its sequel, where an alien civilization manipulates the dimensions of a neutron star, and later a micro-universe is created using the energy of one. Here, the neutron star transcends its natural role, becoming a tool or a component in a cosmic-scale engineering project, reflecting our own dreams of one day harnessing the fundamental forces of the cosmos. Perhaps the most poignant and recurring motif is the pulsar as a celestial lighthouse or a message in a bottle. Its perfectly regular, rhythmic pulses naturally evoke the idea of communication. This was the central premise of the original Planet of the Apes film, where a runaway astronaut crew follows a distress signal that leads them to a shocking revelation on a future Earth. The signal, though of human origin in that story, plays on the same sense of wonder and mystery that real pulsar signals first elicited. In other stories, a pulsar's beat becomes a natural metronome, a universal clock by which galactic civilizations might set their calendars, or a beacon system for charting interstellar trade routes. This transforms the galaxy from a dark, empty void into a navigated space, lit by the steady, reliable heartbeat of these distant sentinels. It connects back to our ancient past when mariners used the stars to guide their wooden ships across uncharted oceans, now projected onto a galactic canvas. This cultural resonance is a testament to the power of astronomy to inspire not just scientists, but artists, writers, and dreamers. The journey of a neutron star from a theoretical curiosity to a baffling signal mistaken for aliens to a well-understood physical phenomenon, and finally to a staple of science fiction, mirrors our own evolving relationship with the cosmos. These fictional depictions, while taking creative liberties, serve a vital purpose. They make the esoteric science of quantum degeneracy pressure and relativistic gravity tangible and exciting. They provide a narrative bridge, allowing a general audience to grasp the sheer scale and power of these objects in an intuitive, emotional way. When a viewer watches a spaceship narrowly escape a pulsar's beam or a character speaks of mining a magnetar for energy, they are engaging with real astrophysical concepts, simplified and dramatized for storytelling, but rooted in our genuine, relentless quest to understand the universe's most extreme creations. But to truly unlock the deepest secrets hidden within these stellar cinders, we need to venture beyond general relativity and even the familiar rules of atomic nuclei, and into the bizarre, colorful world of quantum chromodynamics, or QCD. This is the fundamental theory that describes the strong nuclear force, the incredibly powerful glue that holds quarks together to form protons and neutrons, and then holds those protons and neutrons together to form the nuclei of every atom in the universe. Here on Earth, we study this force in massive particle accelerators like the Large Hadron Collider, where we slam particles together at incomprehensible speeds to momentarily recreate the searing conditions of the early universe. But these experiments are fleeting, lasting less than a blink of an eye, and they create a hot, chaotic soup of quarks and gluons that rapidly cools and condenses back into normal matter. A neutron star offers something completely different and utterly unique. A vast, stable, and naturally occurring laboratory where matter is permanently crushed into a state where the very rules of QCD are pushed to their absolute breaking point. Imagine trying to understand the properties of water. You could study a single, individual molecule, or you could observe a gentle stream. But to truly understand its behavior, you would need to see it under extreme pressure, deep in the ocean, or frozen into a giant, perfect iceberg. A neutron star is that perfect iceberg for the strong force. Its interior is a place of such astronomical density and pressure that the very identity of the neutrons themselves begins to blur and break down. In normal matter, the space between atomic nuclei is immense on a subatomic scale, but inside a neutron star, that empty space has been entirely eliminated. The neutrons are packed together so tightly that they are practically touching, and their swirling, probabilistic quark clouds begin to overlap. Under these conditions, the concept of individual neutrons starts to lose all meaning. Instead of a sea of distinct particles, the core may transition into a continuous, unified state where quarks themselves are deconfined, flowing freely in a soup known as quark matter. This presents a phenomenal opportunity to test QCD in a regime of density and pressure that is simply unreachable in any terrestrial experiment. Our particle colliders create a hot, dense state of quark-gluon plasma, but a neutron star's core is a cold, dense state. This distinction is crucial. The cold, dense environment allows for the potential formation of entirely new, exotic phases of matter that theorists can only dream of creating on Earth. For instance, the quarks, which normally come in pairs or triplets, might pair up in a way that creates a color superconductor, a material that conducts charge with zero resistance, but on a scale and efficiency that dwarfs any earthly superconductor. The properties of such a phase would be dictated purely by the fundamental constants and equations of QCD, and a neutron star's behavior would be the only observable signature we could use to confirm its existence. The way we probe this quantum laboratory from light years away is by connecting these microscopic theories to macroscopic, observable properties of the star. The key relationship is between the star's mass and its radius. Think of it like this: the equation of state, the theoretical description of how matter responds to pressure that comes directly from QCD, acts as a universal recipe. A soft equation of state, which might describe a core of free-flowing quarks, would mean that adding more mass to the star causes it to compactify significantly, resulting in a very small radius for a high-mass star. A stiff equation of state, where matter strongly resists further compression, would allow a massive star to maintain a much larger size. So when astronomers use X-ray observations of binary systems or the gravitational waves from mergers to measure a neutron star's mass and radius, they are not just collecting celestial statistics. They are taking a direct measurement of the stiffness of the densest matter in the universe, which in turn tells us whether the quarks inside are still confined within neutrons or have broken free into an exotic, deconfined soup. Every new data point is a vote for or against the myriad theoretical models of QCD under extreme conditions, allowing us to perform fundamental physics experiments by simply observing the quiet spin or violent collision of these distant cosmic beacons. Looking ahead, the future of neutron star research promises to be even more revolutionary than its past, with a new generation of observatories set to launch that will transform these distant points of light from objects of mystery into open books of fundamental physics. We are on the cusp of moving from simply detecting these cosmic powerhouses to routinely and precisely measuring their most intimate properties. Leading this charge is the European Space Agency's Athena mission, the advanced telescope for high-energy astrophysics, slated for launch in the mid-2030s. This isn't just an incremental upgrade, it's a leap of comparable magnitude to the jump from the first X-ray telescopes to the Chandra Observatory. Athena's key instrument will have a collecting area more than 10 times larger than Chandra's, allowing it to gather X-ray photons with breathtaking efficiency. This means that instead of needing long, painstaking exposures to study the faint thermal glow of a distant neutron star's surface, Athena will deliver high-precision data in a fraction of the time. It will be able to measure the tiny gravitational redshift imprinted on the X-ray spectrum of hundreds of neutron stars, not just a handful, finally providing a massive statistical dataset of their masses and radii. This will allow us to definitively pin down the elusive equation of state of ultra-dense matter, revealing whether neutron star cores are made of neutrons, free quarks, or something even stranger. Athena will also watch the flickering X-ray bursts from binary systems with unparalleled clarity, essentially making a high-definition movie of thermonuclear explosions on the surface, which will act as direct probes of surface gravity and crust composition. Simultaneously, a new sense will be added to our cosmic perception with the launch of the Laser Interferometer Space Antenna, or LISA. This is not a telescope in the traditional sense, but a gravitational wave observatory that will operate in space. While ground-based detectors like LIGO and Virgo listen for the high-frequency chirps of merging neutron stars, LISA will open up the low-frequency gravitational waveband, allowing us to hear the universe's constant rumbling hum. For neutron stars, this is a game-changer. LISA will be able to detect the gravitational waves from millions of binary systems containing neutron stars and white dwarfs long before they merge. It will essentially provide a pre-merger sensors, tracking their slow, in-spiral orbits for years. This will give us an exquisitely precise map of the binary population in our galaxy. More spectacularly, LISA could detect the continuous, low-frequency hum generated by the tiny mountains on rapidly spinning neutron stars. Measuring this steady signal would directly tell us the height of those centimeter-scale deformations, revealing the ultimate breaking strain of the neutron star crust, a fundamental property of matter under extreme pressure that we can never replicate on Earth. LISA might even catch the gravitational waves from a nearby, isolated magnetar as it experiences a colossal starquake, giving us a direct look at the interior dynamics during one of the universe's most energetic seismic events. The synergy between these upcoming missions will create a powerful new paradigm of multi-messenger astronomy. Imagine LISA detecting the faint, early gravitational wave hum of a neutron star binary system in a distant galaxy, providing a prediction that they will merge in several years' time. Astronomers could then point Athena at this system to study the X-rays produced by the accretion process and the tidal heating as the stars spiral closer. When the merger finally happens, ground-based gravitational wave detectors would catch the high-frequency finale, while Athena and optical telescopes would capture the brilliant kilonova aftermath. This coordinated, long-term observation of a single source, from its quiet orbital dance to its cataclysmic end, would provide a complete, holistic picture of a binary neutron star's life cycle, testing our models of gravity, nuclear physics, and stellar evolution all at once. Beyond these flagship missions, other powerful tools are joining the hunt. The Square-Kilometer Array radio telescope will listen for pulsar signals with such sensitivity that it could discover thousands of new millisecond pulsars, effectively mapping the galactic gravitational field and using them to detect the background rumble of gravitational waves from supermassive black hole mergers throughout cosmic history. The Vera C. Rubin Observatory will repeatedly scan the entire sky, likely catching the light curves of many more kilonovae, building a statistical understanding of how often these cosmic gold factories occur. And NASA's Nancy Grace Roman Space Telescope will provide exquisitely deep infrared views, crucial for studying the red light of kilonovae that are obscured by cosmic dust. The questions these future observatories aim to answer are as profound as the technology itself. They will finally tell us what happens to matter when it is crushed beyond the density of an atomic nucleus, settling the debate over the true nature of the neutron star core. They will test whether Einstein's theory of general relativity holds perfectly in the ultra-strong gravity of a merger, or if we see subtle deviations that point toward new physics. They will precisely measure the expansion rate of the universe using gravitational waves, potentially resolving the Hubble tension that currently puzzles cosmologists. And they will determine the detailed astrophysical conditions that forge the heaviest elements, telling us the relative importance of neutron star mergers versus other potential sites like rare supernova in creating the gold, platinum, and uranium that make up our world. We are not just building bigger telescopes, we are constructing portals to a deeper layer of reality, where the most extreme objects in the cosmos will finally reveal their deepest secrets, fundamentally reshaping our understanding of the universe and our place within it. And that brings us to one of the most solitary existences imaginable in the cosmos, the intergalactic neutron star. While many of these stellar remnants are found within the bustling star cities of galaxies, a significant number have been cast out, destined to wander the profound and empty darkness between galaxies. These are the ultimate rogue travelers, stellar ghosts ejected from their homes and set on a course that will take them through a void so vast and empty that the nearest star may be millions of light years away. Their journey begins with the most violent of goodbyes. As we've seen, the supernova explosions that create neutron stars are often asymmetrical, giving the newborn stellar corpse a powerful kick. In the most extreme cases, this natal kick is so forceful that it exceeds the escape velocity of not just the star's local cluster, but of the entire host galaxy itself. Imagine a cosmic cannon where the recoil from an uneven explosion fires a city-sized object with the mass of a sun at thousands of kilometers per second, launching it on a trajectory that will forever sever its ties to the galactic community it was born in. Once it crosses that gravitational threshold, there is no return. The star leaves behind the light and warmth of its galactic home, entering the intergalactic medium, a realm of near-total nothingness where the density of matter can be less than a single atom per cubic meter. Here, it will drift for billions of years, a lone beacon in an ocean of darkness, its spin slowly winding down as it journeys toward oblivion. The very existence of these intergalactic exiles tells us something crucial about the raw power of stellar death. The fact that we can infer their presence means that supernova kicks must be powerful enough to routinely achieve these hypervelocities. This places tight constraints on the physics of core collapse, revealing that the chaos of a star's final moments can be imbalanced enough to literally shoot its remnant clear out of a galaxy. By studying the trajectories of the ones we can detect, we can work backwards to understand the distribution of kick velocities, piecing together the typical forces at play in these cosmic catapults and identifying which types of supernova are most likely to produce such dramatic ejections. This profound isolation, while lonely, is also these neutron stars' greatest scientific gift. An intergalactic rogue is a pristine laboratory, utterly unaffected by the contaminating light, gas, and dust of a host galaxy. When we observe a pulsar within the Milky Way, its signal must travel through our galaxy's turbulent interstellar medium, which can scatter and distort its radio pulses. But the signal from an intergalactic pulsar travels for millions of years through an almost perfect vacuum. This gives us an incredibly clean, unaltered view of the pulsar's intrinsic properties. We can study its pulse profile, its timing stability, and its magnetic field with a clarity that is simply impossible for its galactic cousins. It's like trying to study the sound of a single instrument in the middle of a roaring rock concert versus hearing it played in a silent, echoic chamber. This purity allows for exquisitely precise tests of fundamental physics, such as using their perfectly regular pulses to search for the subtle stretching of spacetime from low-frequency gravitational waves that wash over the entire universe. Furthermore, these isolated wanderers offer a unique opportunity to study the neutron star itself without any complicating factors. There is no binary companion to transfer mass and spin it up, no surrounding supernova remnant to interact with, and no accretion disk to produce confusing X-ray emissions. What we observe is the bare, unadorned neutron star, cooling down and spinning down according to its own internal clock and composition. By measuring the temperature of these ancient, isolated objects, we get a direct read on the efficiency of their internal cooling mechanisms, which in turn reveals secrets about the exotic particles or superfluid states that might exist in their cores. A cold, intergalactic neutron star is a direct probe of the physics of ultra-dense matter in its most quiescent and undisturbed state. Finding these needles in the cosmic haystack is, as you can imagine, one of astronomy's greatest challenges. They are incredibly faint and their positions are unpredictable. Searchers often rely on scouring large sky surveys for point-like sources of X-rays that have no visible galactic counterpart. When a candidate is found, follow-up observations with the most powerful telescopes are needed to measure its distance and confirm its intergalactic status. Each discovery is a monumental achievement, a glimpse of a fossil from an ancient cataclysm that occurred long before our sun was even a glimmer in a galactic cloud. These lonely sentinels are the silent witnesses to the violent history of star formation and death, their uninterrupted journeys carrying them through the darkest and most empty regions of the cosmos, holding within their dense hearts the unaltered story of their own incredible birth. This fascinating connection between neutron stars and the search for extraterrestrial intelligence brings our journey full circle, back to that moment in 1967 when a young Jocelyn Bell Burnell first noticed a bit of scruff on her chart recorder. The initial, thrilling possibility that the perfectly regular pulses from CP1919 might be a beacon from an advanced civilization was a powerful reminder of how the universe constantly challenges our assumptions. While that specific signal turned out to be natural, the experience profoundly shaped the field of SETI, providing a crucial cosmic reference point. It established a baseline for what a highly advanced technological signal might look like: persistent, precisely timed, and originating from deep space. This means that every time a radio telescope detects a new, repeating cosmic rhythm, astronomers must perform a careful dance of analysis, ruling out the natural lighthouse effect of a pulsar before any more exotic possibilities can be considered. In a way, pulsars act as the ultimate control group for the search for intelligent life, the known natural phenomena we must eliminate to find the truly unknown. The very characteristics that make pulsar signals so compelling also provide a masterclass in what to look for in a potential artificial transmission. The pulses from a spinning neutron star exhibit what scientists call a high degree of coherence. This means the signal is concentrated in a very narrow band of frequencies, creating a pure, clear tone in the cosmic static, much like a single, sustained note from a flute standing out against the roar of a waterfall. This coherence is a hallmark of both natural pulsars and what an engineered signal might aspire to be. Furthermore, the timing is unbelievably stable. Millisecond pulsars, in particular, have rotational periods that are constant to within a fraction of a microsecond over decades, a level of precision that screams of a fundamental clockwork process. When SETI scientists design algorithms to sift through vast amounts of data, they often search for this specific combination, a signal that is both spectrally narrow and persistent over time. The universe, through pulsars, has essentially given us a textbook example of an ordered, reliable signal, setting the standard against which any potential hello from another civilization would be judged. This has led to some truly visionary speculation. Could an advanced civilization, one that has mastered interstellar travel or communication, actually use pulsars for its own purposes? Some theorists have proposed that these cosmic lighthouses could serve as a ready-made galactic navigation network, just as we've considered for our own spacecraft. A species spanning multiple star systems might sync their calendars and define their positions relative to the steady ticks of the most stable millisecond pulsars, creating a universal coordinate system that every world in the galaxy could understand. This turns the galaxy from a dark, featureless void into a well-mapped territory, with pulsars acting as the immutable signposts on an interstellar highway. It's a concept that transforms these natural phenomena into foundational elements of a potential galactic culture, a shared utility that any spacefaring civilization would inevitably discover and utilize. An even more profound idea is that a sufficiently advanced society might not just use pulsars, but somehow modify them. Imagine a civilization with technology that reaches the level of what we would consider pure magic. Could they engineer a star? The concept of a stellar engine, a megastructure to harness a star's energy, is a classic trope of speculative science. Applying this to a neutron star, however, takes the idea to an entirely new level of audacity. A neutron star's energy output is already focused and immense. What if a civilization could build a structure, a Dyson sphere of sorts, around a pulsar to capture its entire relativistic wind and radiation beams? Such a feat would provide power on an almost unimaginable scale, perhaps for computational projects or propulsion systems that are beyond our current physics. Even more speculatively, could they artificially induce starquakes on a magnetar to create targeted, incredibly powerful bursts of energy, turning the most volatile object in the universe into a controllable energy weapon or a tool for interstellar engineering? The most direct and tantalizing proposal is that pulsars could be used as a natural interstellar telegraph system. An advanced civilization might not need to build a transmitter of its own if it could simply modulate the signal of an existing one. The idea would be to find a way to slightly alter the pulsar's natural emission in a way that encodes information. This could be done, in theory, by placing a large object in a precise orbit around the neutron star, periodically eclipsing its beam in a complex artificial pattern. Alternatively, a society might deploy a swarm of mirrors or energy-absorbing satellites in the pulsar's magnetosphere, creating a sort of blinking shutter that imposes a message onto the natural pulse. The resulting signal would still look largely like a pulsar to a casual observer, which provides a brilliant camouflage, but to anyone who knew to look for a subtle, intelligent pattern superimposed on the natural rhythm, it would reveal a hidden message. This makes the search for such signals incredibly challenging, as it requires not just finding a pulse, but decoding its most minute irregularities, searching for a signature of intelligence hidden in plain sight, riding on the back of a natural cosmic powerhouse. Ultimately, the relationship between neutron stars and SETI is a story of perspective. They represent both the answer and the question. They are the definitive, natural explanation for one of the greatest false alarms in the history of science, a humbling reminder that the universe is capable of producing phenomena that perfectly mimic our expectations of intelligence. Yet, their very existence and their extraordinary properties continue to inspire us to dream bigger. They show us the kind of raw power and precise clockwork that the cosmos is capable of, setting a bar for what is naturally possible and forcing us to imagine what might lie just beyond it. Every time we listen to the steady tick of a pulsar, we are not only probing the laws of physics at their extreme, but also conducting a subtle, ongoing experiment. We are checking to see if, hidden within that perfect, natural rhythm, there is a whisper of something more, a deliberate signature placed there by a consciousness that looked upon the same cosmic lighthouse and saw not just a star but a tool. So, after journeying through the lives of these incredible stellar titans, from their violent births to their roles as cosmic lighthouses and element forgers, we must finally confront their ultimate, almost philosophical destiny. Our 50th and final fact brings us to the very end of time itself, contemplating the ultimate fate of the universe's neutron stars. Their story does not conclude with a brilliant supernova or a dramatic collision. Instead, it culminates in a fade to black so gradual and profound that it challenges our very conception of existence. Over time frames that make the current age of the universe seem like a single, fleeting heartbeat, these dense remnants will embark on their last, long journey into silence, cooling and darkening until they become little more than frozen, crystalline fossils adrift in an increasingly empty and cold cosmos. This is a narrative that stretches across trillions of years, a future so distant that entire galaxies will have evaporated, and the universe as we know it will be utterly transformed. The first chapter of this final era is one of simple, relentless cooling. A neutron star is born as a searing ember, but its incredible density means it has no ongoing fusion to replenish its heat. It is, in essence, a dying coal in the cosmic fireplace. For the first million years or so, it cools rapidly by emitting neutrinos from its core. But once that furious neutrino emission subsides, the only way left for it to lose heat is by radiating photons from its surface. This process is incredibly slow. Over billions of years, its surface temperature will drop from millions of degrees to just a few thousand, and then, over trillions of years, it will continue to fall. The star once intense X-ray glow will have long since faded through visible light and into the far infrared until finally, it emits no detectable thermal radiation at all. It will become a black dwarf, a solid, ultra-dense sphere of crystallized carbon and iron nuclei with a sea of degenerate electrons flowing through it, hovering at a temperature barely a fraction of a degree above absolute zero. It will be completely dark, invisible against the backdrop of space, its rotation slowed to a near standstill, and its magnetic field faded into insignificance. For all intents and purposes, it will be a frozen monument to a star that died eons ago, a ghost of atomic nuclei locked in a perfect lattice, drifting in perfect silence and perfect darkness. Yet, even this state of frozen perfection may not be the true end of the line. To venture into the absolute farthest future, we must step beyond confirmed physics and into the realm of theoretical particle physics and cosmology. Our current understanding, based on the Standard Model, suggests that a proton, one of the fundamental building blocks of every atomic nucleus, is stable and lasts forever. But many grand unified theories which attempt to merge the electromagnetic, weak and strong nuclear forces predict that the proton is not truly immortal. It should eventually decay with a half-life so astronomically long it is almost incomprehensible. Current experiments have set a lower limit for the proton's lifetime at over 10 to the 34 years, a number with 34 zeros after it. If these theories are correct, then over timescales that dwarf even the cooling of black dwarfs by countless orders of magnitude, the very fabric of the neutron star itself will begin to disintegrate. Imagine that frozen stellar fossil, a perfect crystal of iron nuclei, each nucleus made of protons and neutrons. If protons can decay, then even these nuclei are not eternal. The process would be almost imperceptibly slow. A single proton deep within the star's core would, after an unimaginable duration, spontaneously transform, decaying into a positron and a pion, which would then quickly decay into photons and other light particles. This single event would release a tiny trickle of energy, but across the entire mass of the neutron star, these rare, sporadic decays would represent the final, slow-motion dissolution of the object itself. Over epochs that are literally beyond human imagination, the entire structure would gradually evaporate from the inside out, its immense mass converting into a faint, steady drizzle of radiation and light particles. The incredibly dense crystal lattice would slowly lose its integrity, its perfect order breaking down as its fundamental building blocks vanished one by one. What would be left after this final evaporation? If proton decay is the ultimate rule, then every neutron star, and indeed every piece of normal matter in the universe that hasn't already been consumed by a black hole, would eventually share this fate. The universe would enter a final era known as the Dark Era, an epoch of profound emptiness and darkness. There would be no more stars, no more galaxies, and no more stellar remnants. The cosmos would be a vast, expanding void, populated only by the fleeting products of particle decay and the immense, ancient black holes that had long since stopped accreting any new material. It is a stark and humbling vision of an end that is not a fiery cataclysm, but a slow, cold, and quiet fade into nothingness, where even the most resilient and durable objects in the universe are not permanent, but are merely temporary features in an epic whose final chapters are written in the slow but inevitable decay of the very particles that make up our reality. This ultimate fate transforms the neutron star from a symbol of extreme power and endurance into a poignant reminder of the transitory nature of all structures, no matter how seemingly eternal in the grand, evolving tapestry of the cosmos. Even after journeying through 50 astonishing facts about these cosmic powerhouses, we are left standing at the frontier of our own understanding, humbled by the profound mysteries that still shroud neutron stars. For all the brilliant minds and advanced technology dedicated to their study, these stellar cinders continue to guard their most intimate secrets with a fierce and enigmatic silence. The journey of discovery is far from over. In many ways, it has only just begun, propelled by the very questions we have yet to answer. What, then, are the grand, unresolved puzzles that keep astrophysicists awake at night, staring at data and equations that push the very limits of known physics? At the very heart of the matter, quite literally, lies the greatest enigma of all, the true state of matter in the neutron star core. We've theorized about neutron superfluids, proton superconductors, and exotic soups of free-roaming quarks, but we still lack the definitive proof to crown one of these bizarre states as the victor. Is the core a perfect, frictionless quantum liquid where neutrons flow without any viscosity whatsoever? Or has the pressure become so overwhelmingly powerful that it has shattered the neutrons themselves, creating a new, fundamental state of quark matter that is more stable than anything else in the universe? This isn't just an academic debate. The answer would rewrite our understanding of nuclear physics and reveal the behavior of matter under conditions that can never, ever be recreated in a laboratory on Earth. Every observation of a cooling neutron star, every gravitational wave from a merger, is a new piece of evidence in this cosmic trial, but the jury is still out, and the final verdict remains one of the most sought-after prizes in all of science. Tied directly to this is the quest to pinpoint the ultimate cosmic weight limit, the maximum mass a neutron star can bear before it loses its battle with gravity. We call this the Tolman-Oppenheimer-Volkoff limit, and its precise value is a holy grail for theorists. Current estimates place it somewhere between 2.1 and 2.3 times the mass of our Sun, but that range of uncertainty represents a chasm in our understanding. Finding a neutron star with a mass of, say, 2.4 solar masses would instantly vaporize entire families of theoretical models that rely on a soft, compressible equation of state. It would tell us that matter at these densities is incredibly stiff, stubbornly resisting collapse. Conversely, if we find that all neutron stars seem to cluster below 2.1 solar masses, it would be powerful evidence for a softer interior, perhaps one dominated by free quarks or other exotic particles that give way more easily. This isn't just about setting a record, it's about drawing the final line in the sand between a neutron star and a black hole, defining the ultimate boundary where matter, as we know it, ceases to exist. Then there is the raw, untamed power of the magnetar, whose magnetic fields defy all earthly intuition. We understand the basic principle of magnetic flux conservation, how a star's initial field gets compressed during its collapse. But the details of how these fields are generated, sustained, and ultimately decay remain deeply puzzling. What is the exact dynamo mechanism inside a newly born neutron star that can amplify a magnetic field to 1,000 trillion times the strength of Earth? How is this apocalyptic energy stored and structured within the star's superfluid interior and solid crust? The sudden, violent starquakes and giant flares suggest that these fields are twisted, tangled, and under immense stress. But mapping this invisible architecture from light years away is a monumental challenge. We see the spectacular outbursts, the flashes that can affect our own planet's atmosphere, but the precise trigger and the detailed physics of the magnetic reconnection that powers them are still active and fervent areas of research. Beyond these core mysteries, other puzzling questions beckon from the darkness. What is the ultimate origin of the bizarre fast radio bursts that we now know can come from magnetars? Are all FRBs produced by these magnetic monsters, or are there other, even more exotic engines capable of such brilliant millisecond flashes? The repeating FRBs, with their unpredictable and complex patterns, suggest a system that can store and release energy in ways we don't yet fully comprehend, possibly involving interactions with a companion star or a highly dynamic magnetosphere. And what of the lonely, intergalactic neutron stars? How many of these hypervelocity exiles are drifting through the void between galaxies? And what can their isolated, pristine signals tell us about the fundamental properties of matter, free from any contaminating influence? Each of these questions is a path leading deeper into the unknown, a reminder that for every answer we uncover, the universe presents us with 10 new, more fascinating riddles to solve. The study of neutron stars is a perpetual journey, a conversation with the cosmos where the next great discovery is always just one observation, one simulation, one brilliant insight away. And so, our voyage across the cosmos to explore the universe's most distant and mysterious neutron stars draws to a close. We have journeyed from the cataclysmic fury of their supernova births, through the mind-bending physics of their city-sized, mountain-heavy forms, and out to the very frontiers of our observational capabilities, where these stellar ghosts pulse from billions of light years away. We've witnessed them as cosmic lighthouses, their precise ticks guiding future navigators, as celestial forges creating the very gold in our jewelry in violent collisions, and as nature's ultimate particle accelerators firing cosmic rays across the galaxy. We've delved into the exotic mysteries of their interiors, where matter is crushed into quantum soups of quarks and superfluids, and stood in awe of magnetars, whose twisted magnetic fields could erase a planet's data from half a galaxy away. Each of these 50 facts is a thread in a grand tapestry, weaving together a story that stretches from the death of the first stars to the far future of the cosmos itself. This journey is about far more than just cataloging bizarre astronomical objects. It is a profound demonstration of humanity's relentless curiosity and our place in the universe. By studying these distant, dense remnants, we are not merely looking at faint points of light. We are conducting fundamental physics experiments on a cosmic scale. A neutron star is a natural laboratory for conditions that cannot be recreated on Earth, allowing us to probe the laws of quantum chromodynamics, test Einstein's theory of general relativity with incredible precision, and explore the very nature of space and time. They are our window into the behavior of matter at its absolute limit, teaching us about the strength of the nuclear force, the birth of the elements, and the history of stellar evolution. In their rhythmic pulses and brilliant flares, we find the answers to age-old questions and, inevitably, new, deeper mysteries that push the boundaries of our knowledge. These incredible objects remind us that the universe is a place of both breathtaking beauty and unimaginable power. They are the ultimate symbols of transformation born from death. They become beacons of creation and discovery. The next time you find yourself under a clear, dark night sky, look up. Consider that in the vast, silent depths between the stars you can see with your naked eye, there are untold numbers of these cosmic powerhouses. Each one is a spinning cinder, a dense fossil holding the secrets of a star's final moments, a natural clock of phenomenal precision, and a potential key to understanding the most fundamental forces that shape our reality. Their light, which began its journey to Earth millions or even billions of years ago, is a direct connection to the cosmos's most extreme and creative processes. The exploration is far from over. With revolutionary new telescopes like the James Webb Space Telescope, the Square Kilometre Array, and the upcoming Athena and Lisa missions, we are on the cusp of discoveries that will once again reshape our understanding. We will find more of these distant sentinels, listen more closely to the gravitational waves from their mergers, and perhaps finally unlock the definitive secret of what lies at their hearts. The story of neutron stars is still being written, and each new chapter promises to be more astonishing than the last. If this journey through the cosmos has ignited your sense of wonder, if it has made you look at the night sky with new eyes, then we invite you to join us for more deep dives into the universe's greatest mysteries. Subscribe to the channel and hit the notification bell so you don't miss our next adventure to the frontiers of space and physics. The universe is full of wonders, and together we will continue to explore them all.